Part 2. Why most of the universe is already so cold. If the Boomerang Nebula feels like an impossible place, a ghostly exception to the rules, the next truth is perhaps even stranger. The universe does not need very many special tricks to become cold. In fact, cold is already the natural background condition of deep space. Heat, in the cosmic sense, is the exception. Warmth is local. Fire is local. Sunlight is local. The stars feel grand to us because we live beside one, but in terms of sheer volume, they are tiny islands in an ocean of darkness. And once you drift far enough away from those islands, away from suns and atmospheres and glowing planets, the universe settles into a stillness so deep that even the idea of temperature starts to feel abstract. So after meeting the coldest known natural place, it helps to step back and ask a quieter question. What is the normal temperature of the universe when nothing dramatic is happening? What does space tend to become when it is left alone, when no nearby star is pouring energy into it, when no planet is holding onto warmth, when no violent collision is stirring the gas? The answer is not absolute zero. It is not perfect emptiness. It is something more subtle, and in a way more beautiful. The universe has a background glow, a faint leftover warmth from its own beginning. And that soft afterglow is what sets the thermal mood for almost everything far from a major heat source. If this kind of calm journey into the deep structure of reality helps you unwind, you can support the channel in the gentle way that always helps most, by liking the video, subscribing, and maybe sharing where in the world you're listening from tonight. It is always quietly amazing to imagine these thoughts traveling across bedrooms, cities, coastlines, forests, and quiet roads while we all think about the same cold universe together. To understand why space is so cold, we have to begin with a very different universe. Not the dark one we know now, but the early one. There was a time when the universe was not cold at all. It was blindingly hot, dense, brilliant, and young. In those first moments after the Big Bang, there were no stars, no galaxies, no empty black stretches between them. Everything was compressed together in a state of extraordinary energy. Matter and light were tangled up in a hot plasma. If you could have somehow stood there, which of course you could not, you would not have seen darkness. You would have seen a universe that glowed everywhere. And then it expanded. That simple sentence carries an almost impossible amount of history inside it. The universe expanded yesterday. It expanded while you were eating dinner. It expanded while ancient civilizations rose and disappeared. And it is expanding now while these words pass through your mind. Space itself has been stretching for about 13.8 billion years. And when space stretches, the light traveling through it stretches too. The wavelengths get longer. The energy gets thinner. The temperature associated with that radiation drops. So the original searing brightness of the young universe did not simply vanish. It faded. It cooled. It was stretched across time until it became something much softer, much quieter, and much colder. That remnant is what we call the cosmic microwave background, or CMB. It fills all of space. It is not concentrated in one direction. It does not come from one galaxy or one star. It comes from everywhere at once because it is the surviving echo of the universe when it first became transparent. Today that glow has a temperature of about 725 Kelvin, which is about -274 degrees Celsius, or -454.8 degrees Fahrenheit. That is only a few degrees above absolute zero. It is hard to really feel what that number means, because human intuition is built for kitchens and winters and summer heat, not for a temperature so low that ordinary language begins to lose its grip. But this is one of the most important ideas in all of cosmology. Even in the deepest darkness, space is not perfectly black in a thermal sense. It is full of this faint relic radiation. If you placed an object in deep space, very far from stars and other heat sources, and simply let it sit there for a long enough time, it would not cool all the way to absolute zero. It would eventually drift toward the temperature of that background glow. The universe has, in a sense, a minimum ambient hum, a thermal whisper left over from creation. There is something quietly poetic about that. The cosmos remembers heat. Even now, long after the first stars were born and long after galaxies spread across unimaginable distances, every corner of space still carries a trace of the beginning. If your eyes were somehow sensitive to microwaves instead of visible light, the sky would never truly go dark. In every direction, day or night, through every empty region between the stars, you would see the afterglow of the early universe surrounding you. Not bright, not dramatic, just a soft, nearly uniform shell of ancient warmth, wrapped around all things. And yet, when we say the universe is cold almost everywhere, we have to be careful about what we mean. We do not mean that every atom in the cosmos sits at 2.7 Kelvin. Some gas between galaxies is surprisingly hot, even while being incredibly thin. Some regions near black holes blaze with terrifying energy. Some stars burn at millions of degrees in their cores. There are violent pockets of heat all across the universe. But they are pockets. They are events. They are local weather in an overwhelmingly vast cosmic geography whose baseline is cold. The more honestly you zoom out, the more you realize that warmth lives in scattered furnaces, while the background stage remains dark and frigid. This is one reason the stars matter so much. A star is not just a bright object. It is a rebellion against the cold. It is gravity gathering matter tightly enough to ignite fusion, making a local zone where temperature suddenly surges far above the cosmic backdrop. Our sun feels like the center of everything because, for life on Earth, it basically is. It warms the oceans, drives the weather, feeds plants, shapes days and seasons, and defines what comfort even feels like for us. But on a cosmic map, the sun is one small lantern in a galaxy of hundreds of billions of stars, and that galaxy is one among hundreds of billions, perhaps more. Between those lanterns, the dark remains immense. Imagine leaving Earth. First you rise through the atmosphere, where air still clings to the planet and helps hold heat near the surface. Then you move beyond low orbit, past the familiar brightness of home. The sun is still powerful there, of course. Sunlight still pours across space. But step by step, object by object, you begin to notice a pattern. Warmth is strongest where something intercepts light, stores it, and shares it. A planet with an atmosphere can trap heat. A moon with dark rock can absorb sunlight on one side and radiate it away on the other. A spacecraft in sunlight can become dangerously hot, while a shaded panel on the same craft can become bitterly cold. Already, the old idea of space as simply freezing starts to break apart. Space is not a cold substance touching everything equally. It is a stage where heating and cooling depend on radiation, shadow, exposure, and time. The moon is a good example. Under full sunlight, its surface can become extremely hot. But in permanently shadowed craters near its poles, where sunlight almost never reaches, temperatures can plunge to around 25 Kelvin. That is colder than Pluto's average surface. Mercury, surprisingly, can also hide regions of deep cold in crater floors near its poles, despite living so close to the sun. These places feel almost paradoxical. A world can be roasted on one side and preserve pockets of ancient cold in another, simply because geometry and shadow matter so much in space. Move farther outward, past the orbits of the inner planets, and sunlight weakens with every step. By the time you reach Jupiter and Saturn, the sun is still bright, but it is no longer the overwhelming presence it is here. Beyond them, Uranus and Neptune circle in a dimmer kingdom. And beyond those planets lies a region where sunlight becomes more suggestion than command. Out there, on icy bodies and drifting debris, the cosmic background does not dominate completely, but the universe begins to look far more like its true self: sparse, dark, and cold. Still, the real lesson arrives only when we leave the solar system altogether. Once the sun becomes just another star behind you, its warmth fades into the wider galactic sea. Interstellar space is not totally empty. It contains gas, dust, magnetic fields, cosmic rays, and the pervasive glow of the CMB. but it is astonishingly thin. A laboratory vacuum on Earth can contain vastly more particles than a typical region between stars. The emptiness is so profound that ordinary comparisons almost fail. In that vastness, there is little material to hold heat, little material to share it, and little to interrupt the gradual tendency of isolated things to cool by radiating energy away. This is why the deep universe feels thermally quiet. On Earth, temperature is a social property. Molecules crowd one another. They collide constantly. Heat moves quickly through air, water, metal, stone, skin. Space is different. Space is lonely. A hot object can stay hot for a while if there is little around it to steal or share energy, but it will still radiate heat away. A cold object can remain cold because there is so little around it to warm it. The vacuum does not freeze things by touching them. It simply offers very few ways for warmth to return once it has been radiated into the dark. And over great timescales, that matters. Cosmic temperatures are often a story of patience. Given enough time, enough isolation, and enough distance from major energy sources, objects settle downward. They cool. They darken. They become quieter. Young stars blaze. Dead stars fade. Hot worlds lose internal heat. Even galaxies, magnificent as they are not uniformly warm cities of light. Most of their volume is darkness threaded between stars. There is a strange comfort in that idea. The universe is not mostly made of fireworks. It is mostly made of intervals. Between one source of brightness and the next, there are long stretches where almost nothing happens quickly. This helps explain why the Boomerang Nebula is so fascinating. It is not interesting because it exists inside a warm universe. It is interesting because it managed to become even colder than a universe that is already, at baseline, nearly frozen. One of the most interesting facts about the cosmic microwave background is that it used to be much warmer. If you go back in time, the whole universe was hotter because the background radiation had not yet been stretched so much by expansion. A billion years ago, the CMB was warmer than it is now. 10 billion years ago, warmer still. In the deep future, if the expansion continues, the background temperature will keep dropping. The universe is cooling overall not because someone is turning down a dial, but because space itself is widening, thinning the energy it contains. The great chill of the cosmos is, in a very real way, a story about geometry. You can think of it like music played across an ever-growing hall. The melody is the same melody, but as the hall stretches wider and wider, each note becomes more drawn out, softer, less intense. The song remains, but the energy per note keeps falling. The afterglow of the Big Bang has been stretched like that for billions of years, until it now whispers in microwaves. There is another gentle surprise hidden in all this. The night sky looks black to our eyes, but blackness can be deceptive. We associate darkness with emptiness and emptiness with zero. Yet the sky is not zero. The darkness is alive with low-energy light our eyes cannot see. And even the darkness itself tells a story. If the universe were eternal, static, and filled uniformly with stars, the whole sky would blaze as bright as a stellar surface. The fact that it does not is a clue that the universe has a history, that stars are finite, that space expands, and that the visible lights of galaxies are scattered across vast distances. So the darkness above us is not just an absence. It is evidence. This is one of the quiet joys of astronomy. Things that seem simple at first begin to deepen the longer you sit with them. Cold is not merely cold. Darkness is not merely darkness. Empty space is not truly empty. The black between stars is carrying information. It is carrying age. It is carrying the faint heat of the first fire. And yet, for all this grandeur, the real emotional force of cosmic cold may come from scale. On Earth, cold is usually a local thing. A winter morning. A deep freezer. A mountain night. You step indoors, light a fire, wrap yourself in a blanket, and the cold becomes manageable because the environment is small enough to escape. But the cold of the universe is not arranged around human comfort. There is no outside and inside in the same sense. There are only regions of relative warmth floating inside an ocean whose natural resting state is almost at the floor of temperature itself. That is the part the mind struggles to picture. Not just the number, but the size of the number's domain. It is one thing to say 7 Kelvin. It is another to remember that this background extends everywhere. Between the stars of our galaxy. Between our galaxy and its neighbors. Through clusters, filaments, and remote regions where no human being will ever travel. The universe's low-temperature backdrop is not a detail. It is the setting. It is the wallpaper behind every galaxy and every dark cloud. And because the distances are so enormous, the cold is not just intense. It is patient, ancient. In some places it has endured longer than Earth has existed. This gives cosmic warmth a new character too. Heat becomes precious. A star is not just hot, it is a sanctuary from a larger chill. A planet with a thick atmosphere is not just habitable, it is a place where energy is being held against a cosmic tendency toward dispersal. Life itself begins to look like a brief local answer to a very large cold silence. Not in a bleak way, but in a tender one. The warmth of a world like ours feels more miraculous when you remember the background against which it exists. And perhaps that is why space captivates us so easily at night. We look up and sense both things at once, even if we do not always have words for it. We sense the beauty of light, and we sense the depth of the dark around it. We sense islands and ocean together. Maybe that is why starlight feels almost emotional. It is not only brightness. It is brightness surrounded by almost unimaginable cold. As our instruments improve, we keep learning how many forms this cold can take. Some regions are cold because they are hidden from light. Some because they are diffuse and isolated. Some because gas is expanding rapidly, as in the Boomerang Nebula. Some because molecules in dark clouds can shed energy efficiently and sink to very low temperatures. But this is where the story gets more interesting, because a cold number alone does not tell you what kind of place you are dealing with. A shadowed crater, a giant molecular cloud, a shell of expanding gas, and an immense dark region between galaxies can all be called cold, yet they are cold in very different ways. So before we go deeper into the record-breaking extremes, it helps to pause here and hold onto the central truth. The universe does not begin as a warm place that occasionally becomes cold.
It is almost the reverse. The broad cosmic background is already astonishingly close to absolute zero, and warmth appears as a series of temporary local uprisings against that backdrop. Stars, planets, accretion disks, explosions, collisions, hot gas, and living worlds are the vivid exceptions. The larger stage remains dark, thin, and anciently cool. And if you let yourself picture that for a moment, really picture it, the scale becomes almost hypnotic. Countless galaxies suspended in a sea that remembers the Big Bang as a whisper. Worlds circling suns that flare against a background only a few degrees above absolute zero. Invisible radiation passing through every room you have ever lived in, through your body, through the planet beneath you, through the quiet air outside your window, connecting this ordinary night to the earliest era of the cosmos. If this calm journey through the cold architecture of the universe is helping you drift a little deeper, you can leave a quiet like on the video, subscribe for more of these slow cosmic explorations, and share a thought in the comments about which kind of cold feels most mysterious to you so far, the shadowed cold of objects, or the background cold of space itself. Because from here, the next step is an important one. Once we understand that the universe is already cold almost everywhere in the broadest sense, we can ask a more refined question. What exactly are we calling cold? A place? An object? A cloud? A void? A moon in shadow? A dying star's expanding breath? The temperatures may sound similar, but the physical realities behind them are very different. And that difference is where the universe starts to become not just colder, but far more interesting. Part 2: Why most of the universe is already so cold. If the Boomerang Nebula feels like an impossible place, a ghostly exception to the rules, the next truth is perhaps even stranger. The universe does not need very many special tricks to become cold. In fact, cold is already the natural background condition of deep space. Heat, in the cosmic sense, is the exception. Warmth is local. Fire is local. Sunlight is local. The stars feel grand to us because we live beside one, but in terms of sheer volume, they are tiny islands in an ocean of darkness. And once you drift far enough away from those islands, away from suns and atmospheres and glowing planets, the universe settles into a stillness so deep that even the idea of temperature starts to feel abstract. So after meeting the coldest known natural place, it helps to step back and ask a quieter question. What is the normal temperature of the universe when nothing dramatic is happening? What does space tend to become when it is left alone, when no nearby star is pouring energy into it, when no planet is holding onto warmth, when no violent collision is stirring the gas? The answer is not absolute zero. It is not perfect emptiness. It is something more subtle, and in a way more beautiful. The universe has a background glow, a faint leftover warmth from its own beginning. And that soft afterglow is what sets the thermal mood for almost everything far from a major heat source. If this kind of calm journey into the deep structure of reality helps you unwind, you can support the channel in the gentle way that always helps most, by liking the video, subscribing, and maybe sharing where in the world you're listening from tonight. It is always quietly amazing to imagine these thoughts traveling across bedrooms, cities, coastlines, forests, and quiet roads while we all think about the same cold universe together. To understand why space is so cold, we have to begin with a very different universe. Not the dark one we know now, but the early one. There was a time when the universe was not cold at all. It was blindingly hot, dense, brilliant, and young. In those first moments after the Big Bang, there were no stars, no galaxies, no empty black stretches between them. Everything was compressed together in a state of extraordinary energy. Matter and light were tangled up in a hot plasma. If you could have somehow stood there, which of course you could not, you would not have seen darkness. You would have seen a universe that glowed everywhere. And then it expanded. That simple sentence carries an almost impossible amount of history inside it. The universe expanded yesterday. It expanded while you were eating dinner. It expanded while ancient civilizations rose and disappeared. And it is expanding now while these words pass through your mind. Space itself has been stretching for about 13.8 billion years. And when space stretches, the light traveling through it stretches too. The wavelengths get longer. The energy gets thinner. The temperature associated with that radiation drops. So the original searing brightness of the young universe did not simply vanish. It faded. It cooled. It was stretched across time until it became something much softer, much quieter, and much colder. That remnant is what we call the cosmic microwave background, or CMB. It fills all of space. It is not concentrated in one direction. It does not come from one galaxy or one star. It comes from everywhere at once because it is the surviving echo of the universe when it first became transparent. Today that glow has a temperature of about 725 Kelvin, which is about -274 degrees Celsius, or -454, 8 degrees Fahrenheit. That is only a few degrees above absolute zero. It is hard to really feel what that number means, because human intuition is built for kitchens and winters and summer heat, not for a temperature so low that ordinary language begins to lose its grip. But this is one of the most important ideas in all of cosmology. Even in the deepest darkness, space is not perfectly black in a thermal sense. It is full of this faint relic radiation. If you placed an object in deep space, very far from stars and other heat sources, and simply let it sit there for a long enough time, it would not cool all the way to absolute zero. It would eventually drift toward the temperature of that background glow. The universe has, in a sense, a minimum ambient hum, a thermal whisper left over from creation. There is something quietly poetic about that. The cosmos remembers heat. Even now, long after the first stars were born and long after galaxies spread across unimaginable distances, every corner of space still carries a trace of the beginning. If your eyes were somehow sensitive to microwaves instead of visible light, the sky would never truly go dark. In every direction, day or night, through every empty region between the stars, you would see the afterglow of the early universe surrounding you. Not bright, not dramatic, just a soft, nearly uniform shell of ancient warmth, wrapped around all things. And yet, when we say the universe is cold almost everywhere, we have to be careful about what we mean. We do not mean that every atom in the cosmos sits at 2.7 Kelvin. Some gas between galaxies is surprisingly hot, even while being incredibly thin. Some regions near black holes blaze with terrifying energy. Some stars burn at millions of degrees in their cores. There are violent pockets of heat all across the universe. But they are pockets. They are events. They are local weather in an overwhelmingly vast cosmic geography whose baseline is cold. The more honestly you zoom out, the more you realize that warmth lives in scattered furnaces, while the background stage remains dark and frigid. This is one reason the stars matter so much. A star is not just a bright object. It is a rebellion against the cold. It is gravity gathering matter tightly enough to ignite fusion, making a local zone where temperature suddenly surges far above the cosmic backdrop. Our sun feels like the center of everything because, for life on Earth, it basically is. It warms the oceans, drives the weather, feeds plants, shapes days and seasons, and defines what comfort even feels like for us. But on a cosmic map, the sun is one small lantern in a galaxy of hundreds of billions of stars, and that galaxy is one among hundreds of billions, perhaps more. Between those lanterns, the dark remains immense. Imagine leaving Earth. First you rise through the atmosphere, where air still clings to the planet and helps hold heat near the surface. Then you move beyond low orbit, past the familiar brightness of home. The sun is still powerful there, of course. Sunlight still pours across space. But step by step, object by object, you begin to notice a pattern. Warmth is strongest where something intercepts light, stores it, and shares it. A planet with an atmosphere can trap heat. A moon with dark rock can absorb sunlight on one side and radiate it away on the other. A spacecraft in sunlight can become dangerously hot, while a shaded panel on the same craft can become bitterly cold. Already, the old idea of space as simply freezing starts to break apart. Space is not a cold substance touching everything equally. It is a stage where heating and cooling depend on radiation, shadow, exposure, and time. The moon is a good example. Under full sunlight, its surface can become extremely hot. But in permanently shadowed craters near its poles, where sunlight almost never reaches, temperatures can plunge to around 25 Kelvin. That is colder than Pluto's average surface. Mercury, surprisingly, can also hide regions of deep cold in crater floors near its poles, despite living so close to the sun. These places feel almost paradoxical. A world can be roasted on one side and preserve pockets of ancient cold in another, simply because geometry and shadow matter so much in space. Move farther outward, past the orbits of the inner planets, and sunlight weakens with every step. By the time you reach Jupiter and Saturn, the sun is still bright, but it is no longer the overwhelming presence it is here. Beyond them, Uranus and Neptune circle in a dimmer kingdom. And beyond those planets lies a region where sunlight becomes more suggestion than command. Out there, on icy bodies and drifting debris, the cosmic background does not dominate completely, but the universe begins to look far more like its true self. Sparse, dark, and cold. Still, the real lesson arrives only when we leave the solar system altogether. Once the sun becomes just another star behind you, its warmth fades into the wider galactic sea. Interstellar space is not totally empty. It contains gas, dust, magnetic fields, cosmic rays, and the pervasive glow of the CMB. But it is astonishingly thin. A laboratory vacuum on Earth can contain vastly more particles than a typical region between stars. The emptiness is so profound that ordinary comparisons almost fail. In that vastness, there is little material to hold heat, little material to share it, and little to interrupt the gradual tendency of isolated things to cool by radiating energy away. This is why the deep universe feels thermally quiet. On Earth, temperature is a social property. Molecules crowd one another. They collide constantly. Heat moves quickly through air, water, metal, stone, skin. Space is different. Space is lonely. A hot object can stay hot for a while if there is little around it to steal or share energy, but it will still radiate heat away. A cold object can remain cold because there is so little around it to warm it. The vacuum does not freeze things by touching them. It simply offers very few ways for warmth to return once it has been radiated into the dark. And over great timescales, that matters. Cosmic temperatures are often a story of patience. Given enough time, enough isolation, and enough distance from major energy sources, objects settle downward. They cool. They darken. They become quieter. Young stars blaze. Dead stars fade. Hot worlds lose internal heat. Even galaxies, magnificent as they are not uniformly warm cities of light. Most of their volume is darkness threaded between stars. There is a strange comfort in that idea. The universe is not mostly made of fireworks. It is mostly made of intervals. Between one source of brightness and the next, there are long stretches where almost nothing happens quickly. This helps explain why the Boomerang Nebula is so fascinating. It is not interesting because it exists inside a warm universe. It is interesting because it managed to become even colder than a universe that is already, at baseline, nearly frozen. One of the most interesting facts about the cosmic microwave background is that it used to be much warmer. If you go back in time, the whole universe was hotter because the background radiation had not yet been stretched so much by expansion. A billion years ago, the CMB was warmer than it is now. 10 billion years ago, warmer still. In the deep future, if the expansion continues, the background temperature will keep dropping. The universe is cooling overall not because someone is turning down a dial, but because space itself is widening, thinning the energy it contains. The great chill of the cosmos is, in a very real way, a story about geometry. You can think of it like music played across an ever-growing hall. The melody is the same melody, but as the hall stretches wider and wider, each note becomes more drawn out, softer, less intense. The song remains, but the energy per note keeps falling. The afterglow of the Big Bang has been stretched like that for billions of years, until it now whispers in microwaves. There is another gentle surprise hidden in all this. The night sky looks black to our eyes, but blackness can be deceptive. We associate darkness with emptiness and emptiness with zero. Yet the sky is not zero. The darkness is alive with low-energy light our eyes cannot see. And even the darkness itself tells a story. If the universe were eternal, static, and filled uniformly with stars, the whole sky would blaze as bright as a stellar surface. The fact that it does not is a clue that the universe has a history, that stars are finite, that space expands, and that the visible lights of galaxies are scattered across vast distances. So the darkness above us is not just an absence. It is evidence. This is one of the quiet joys of astronomy. Things that seem simple at first begin to deepen the longer you sit with them. Cold is not merely cold. Darkness is not merely darkness. Empty space is not truly empty. The black between stars is carrying information. It is carrying age. It is carrying the faint heat of the first fire. And yet, for all this grandeur, the real emotional force of cosmic cold may come from scale. On Earth, cold is usually a local thing. A winter morning, a deep freezer, a mountain night. You step indoors, light a fire, wrap yourself in a blanket, and the cold becomes manageable because the environment is small enough to escape. But the cold of the universe is not arranged around human comfort. There is no outside and inside in the same sense. There are only regions of relative warmth floating inside an ocean whose natural resting state is almost at the floor of temperature itself. That is the part the mind struggles to picture. Not just the number, but the size of the number's domain. It is one thing to say 7 Kelvin. It is another to remember that this background extends everywhere. Between the stars of our galaxy. Between our galaxy and its neighbors. Through clusters, filaments, and remote regions where no human being will ever travel. The universe's low-temperature backdrop is not a detail. It is the setting. It is the wallpaper behind every galaxy and every dark cloud. And because the distances are so enormous, the cold is not just intense. It is patient, ancient. In some places it has endured longer than Earth has existed. This gives cosmic warmth a new character too. Heat becomes precious. A star is not just hot, it is a sanctuary from a larger chill. A planet with a thick atmosphere is not just habitable, it is a place where energy is being held against a cosmic tendency toward dispersal. Life itself begins to look like a brief local answer to a very large cold silence. Not in a bleak way, but in a tender one. The warmth of a world like ours feels more miraculous when you remember the background against which it exists. And perhaps that is why space captivates us so easily at night. We look up and sense both things at once, even if we do not always have words for it. We sense the beauty of light, and we sense the depth of the dark around it. We sense islands and ocean together. Maybe that is why starlight feels almost emotional. It is not only brightness. It is brightness surrounded by almost unimaginable cold. As our instruments improve, we keep learning how many forms this cold can take. Some regions are cold because they are hidden from light. Some because they are diffuse and isolated. Some because gas is expanding rapidly, as in the Boomerang Nebula. Some because molecules in dark clouds can shed energy efficiently and sink to very low temperatures. But this is where the story gets more interesting, because a cold number alone does not tell you what kind of place you are dealing with. A shadowed crater, a giant molecular cloud, a shell of expanding gas, and an immense dark region between galaxies can all be called cold, yet they are cold in very different ways. So before we go deeper into the record-breaking extremes, it helps to pause here and hold onto the central truth. The universe does not begin as a warm place that occasionally becomes cold. It is almost the reverse. The broad cosmic background is already astonishingly close to absolute zero, and warmth appears as a series of temporary local uprisings against that backdrop. Stars, planets, accretion disks, explosions, collisions, hot gas, and living worlds are the vivid exceptions. The larger stage remains dark, thin, and anciently cool. And if you let yourself picture that for a moment, really picture it, the scale becomes almost hypnotic. Countless galaxies suspended in a sea that remembers the Big Bang as a whisper. Worlds circling suns that flare against a background only a few degrees above absolute zero. Invisible radiation passing through every room you have ever lived in, through your body, through the planet beneath you, through the quiet air outside your window, connecting this ordinary night to the earliest era of the cosmos. If this calm journey through the cold architecture of the universe is helping you drift a little deeper, you can leave a quiet like on the video, subscribe for more of these slow cosmic explorations, and share a thought in the comments about which kind of cold feels most mysterious to you so far, the shadowed cold of objects, or the background cold of space itself. Because from here, the next step is an important one. Once we understand that the universe is already cold almost everywhere in the broadest sense, we can ask a more refined question. What exactly are we calling cold? A place? An object? A cloud? A void? A moon in shadow? A dying star's expanding breath? The temperatures may sound similar, but the physical realities behind them are very different. And that difference is where the universe starts to become not just colder, but far more interesting. Part 3. The difference between cold objects and cold regions. By now, the shape of the universe's cold has started to change a little in the mind. At first it may have seemed simple. Space is cold. That feels easy enough. But the more closely we look, the more that simple sentence begins to unfold into something richer. The universe is not cold in just one way. A frozen moon is cold in one sense. A dark cloud between the stars is cold in another. A vast region between galaxies may be described as cold in a broader, quieter way still. And if we want to understand the true scale of the coldest parts of the cosmos, we need to slow down here and make an important distinction. Not everything cold is the same kind of thing. Some cold things are objects. They have surfaces, boundaries, shapes, and in some cases even weather. A moon can be cold. A planet can be cold. A comet drifting in darkness can be cold. These are places you could, at least in theory, point to and say, there it is. It begins here and ends there. It has an edge. It has a body. It is a world, or a rock, or a frozen sphere with a measurable size. But some cold things are not objects in that neat sense at all. They are regions. A stretch of shadow. A giant cloud of thin gas. A drifting shell of material around a dying star. A volume of space where the temperature is low, but where there may be no solid surface to stand on and no clean border where one place stops and another begins. These are colder not because they are hard, icy things, but because the matter inside them is sparse, dim, and losing energy in a different way. That difference matters more than it may first appear. Because when people hear about the coldest places in the universe, the mind often wants to picture a kind of ultimate ice world. Some giant frozen planet, perhaps, sitting alone in darkness, like an abandoned marble at the edge of reality. That image is understandable. It is also a little misleading. The deepest cold in the universe often does not belong to a classic object at all. It belongs to environments, to conditions, to enormous volumes where matter, radiation, shadow, and expansion work together to create a calm, extreme chill. So before we travel farther outward, it helps to sort the cold into categories the mind can hold gently. Let us begin with cold objects, because they are easier for the imagination. A cold object is something with a body. It might be a moon hidden from sunlight, a distant dwarf planet, an asteroid tumbling in deep space, or a grain of dust drifting in a dark cloud. When we talk about its temperature, we are usually talking about the material itself. How much thermal energy is in the rock, or ice, or dust, or gas that makes up the object. We can ask what warms it, what cools it, how quickly it loses heat, how much sunlight it receives, whether it has an atmosphere, whether it has internal heat, whether it reflects light or absorbs it. Take our own moon. It is not uniformly cold. In sunlight, parts of it become very hot. In darkness, they cool quickly. In permanently shadowed craters near the poles, where sunlight barely reaches if at all, temperatures can sink to astonishingly low levels. Those craters are cold objects in a local sense, parts of a defined world. They are real locations on a solid body. If you mapped them, they would stay where they are. Their cold comes from geometry, shadow, and long isolation from warming light. Mercury gives us another beautiful example. Most people think of Mercury as a scorched world, and in many places it is. It orbits so close to the sun that its sunlit surface can become fiercely hot. But near its poles, in crater floors that remain in permanent darkness, there are places cold enough to preserve water ice. This feels almost like a contradiction. A world near the sun, yet hiding pockets of ancient cold. But it reminds us that object-based cold can be very local. The same object can contain both extreme heat and deep cold, depending on angle, shadow, and time. Then there are distant worlds like Pluto, Triton, or icy bodies in the Kuiper belt. These are objects whose overall environments are much colder because they live far from the sun. Their surfaces receive so little solar energy that ice, frost, and frozen nitrogen can remain stable across vast stretches. Their cold is not just local shadow. It is part of their wider identity as distant, dimly lit bodies. Still, they remain objects. They are things with mass gathered into one body by gravity. They have terrains, horizons. In principle, if you stood there, you would be standing on something. And this is where the imagination often settles, because objects feel familiar. We understand the idea of a place as a thing, a frozen lake, a mountain, a moon, a planet. Even when the temperature is unimaginably low, the concept still belongs to everyday intuition. We know what an object is. But the universe does not limit itself to the kinds of cold we already understand. Now imagine leaving the surface behind entirely. Not standing on a frozen body, but drifting inside a huge, dark cloud between stars. There is no ground, no horizon, no single solid thing to point at. Around you is a thin mixture of gas and dust spread across a region so large that whole solar systems could fit inside it many times over. The temperature is low, not because the cloud is a frozen rock, but because the particles inside it are moving slowly and because the region is shielded from strong sources of heat. This is not a cold object in the usual sense. It is a cold region. That difference changes everything. A cold region can be immense. Much larger than planets, much larger than stars, sometimes larger than the distance between stars. And because it is not a compact body, its temperature is not experienced the way a cold surface is experienced. There is no icy wall, no frozen plain, just a low-energy environment, a quiet volume of space where the matter itself is thin, dim, and spread out. Think of a dark molecular cloud in the Milky Way. These clouds are among the coldest star-forming environments in the galaxy. Their temperatures can fall to around 10 Kelvin, sometimes even lower in protected cores. These are not tiny patches. They can span dozens or even hundreds of light years. Inside them, dust helps block outside starlight, allowing the gas to cool. Molecules drift through darkness. Over vast timescales, gravity slowly gathers parts of the cloud until stars may eventually form. So here we find one of the universe's loveliest paradoxes. Some of the coldest regions are also the birthplaces of future suns. If you tried to compare such a cloud to a frozen moon, the comparison would break down quickly. A moon is compact. The cloud is diffuse. A moon has a surface temperature. The cloud has a regional temperature. A moon is a body. The cloud is an environment. Both may be cold, but they are cold in fundamentally different ways. And this matters for another reason. When astronomers say something is cold, they are often describing the average kinetic energy of particles in a system. In a solid surface, that means atoms in rock or ice vibrating with less energy. In a gas cloud, it means molecules drifting and colliding very slowly. In a diffuse region between galaxies, it may refer to particles so sparse that the concept of temperature becomes subtle, because there is so little matter present to behave collectively in the way we are used to. This is one of those points where the universe gently asks us to stop thinking like creatures of the ground. On Earth, most of our temperature experience comes from touching objects or moving through air. We know cold floors, cold metal, cold rain, cold wind. But in deep space, temperature often belongs to systems that are nothing like the things our bodies evolved to understand. A cold nebula is not cold like an ice cube. A cosmic void is not cold like winter air. The numbers may both be low, but the physical meaning is not the same. The easiest way to feel this difference is to imagine two scenes. In the first scene, you are standing on the dark side of a frozen world. Beneath you is solid ground. Above you is black sky. The surface has spent a long time radiating away its heat. No atmosphere holds warmth in place. The rock and ice beneath you are cold objects. They store little heat. They lose what they have. Their temperature is tied to the body itself. In the second scene, there is no ground at all. You are drifting inside a giant cloud between stars. The cloud is dark, dense by cosmic standards, but still far thinner than any vacuum chamber most people would imagine. Dust grains float like tiny embers gone cold. Molecules drift in a silence that lasts for years between meaningful changes. Here the cold belongs to the region, to the shared environment. It is not the chill of a surface underfoot. It is the calm of an entire volume. Both are cold, but the feeling of the idea is completely different. There is another category that sits between these two and makes the picture even more interesting. Sometimes a cold object creates a cold region around itself. A dying star can blast material outward, forming an expanding shell that cools as it grows. That shell may become colder than nearby space. The Boomerang Nebula is the great example, but it also teaches the broader lesson. The coldest parts of the universe are not always static bodies that simply sit in darkness. Sometimes they are active structures, made by motion. The cold comes not only from distance and shadow, but from a physical process unfolding across a large region. This is one reason the Boomerang Nebula is such a useful guide to the topic. It forces us to stop asking only, what is the coldest object, and start asking, what kind of cold are we talking about? Its most extraordinary cold does not belong to a little frozen stone at its center. It belongs to expanding gas spread across a huge volume. It is regional cold, process-driven cold, not merely object-based cold. And once you begin to see the distinction, you start noticing it everywhere. A comet nucleus is a cold object. The coma around it, under the right conditions, becomes a temporary region with its own thermal behavior. A planet may have a cold surface, but the permanently shadowed crater within it is a colder local region. A dense core of a molecular cloud may be much colder than the larger cloud around it. A galaxy cluster may contain hot gas overall, yet within it there can still be cooler structures, cooler pockets, cooler flows. Cold in the universe is layered. It nests inside itself. This is why scale becomes so slippery. If someone asks, what is colder, Pluto or a dark nebula, the answer depends on which part, under what conditions, measured how, and over what volume. Pluto is a defined cold object. A dark nebula is a cold region. One may have colder local numbers in one sense, while the other is vastly larger and more representative of deep cosmic cold in another. The universe rarely rewards oversimplified rankings. There is also something philosophically quiet about the difference. Objects feel like individuals. Regions feel like moods. A cold object is a thing. A cold region is a state of being extended through space. Perhaps that is part of why cosmic cold feels so haunting. The coldest parts of the universe are not always places with hard outlines. Sometimes they are more like vast conditions lingering across unimaginable distances. And those conditions can shape what comes next. In cold regions, chemistry changes. Molecules that would be unstable in hotter environments can survive longer. Dust grains can collect thin icy coatings. Gas pressure drops, which can allow gravity to slowly take over in certain places. In dark molecular clouds, cold helps prepare the raw material from which stars and planets may one day emerge. So cold regions are not merely empty or dead. They are often preparation rooms for the future. That can be easy to miss when we hear words like freezing, barren, or lifeless. From a human point of view, extreme cold feels hostile. And in direct biological terms, of course it is. But cosmically, cold is not only destructive. It is organizing. It slows things down. It protects fragile molecules from energetic disruption. It allows certain structures to persist. It creates the quiet conditions in which gravity can work patiently over immense spans of time. So if a frozen moon feels like a finished thing, a cold cloud can feel like an unfinished one. One is a world. The other is material waiting to become worlds. There are even larger cold regions that make molecular clouds seem modest by comparison. Consider the spaces between galaxies, or the great cosmic voids where matter becomes sparse across tens or hundreds of millions of light years. These are not always the coldest in the same simple way a shielded cloud core might be. Some intergalactic gas can actually be hot despite being incredibly diffuse, heated by shocks, radiation, or past cosmic violence. So again, the word cold must be handled with care. Low density is not always the same as low temperature. Darkness is not automatically cold in the way intuition wants it to be. Even a void has a thermal story, and sometimes that story is stranger than expected. This is why careful language matters. A cold object is usually easier to define and measure. A cold region often requires asking what matter is present, how dense it is, what radiation passes through it, whether it is expanding, whether dust is shielding it, whether nearby stars are warming it, and whether the particles inside have had enough time to reach something like thermal balance. The numbers may sound straightforward, but the reality behind them is delicate. And yet, for all this complexity, the broader intuition remains beautifully simple once you settle into it. Objects are cold as bodies. Regions are cold as environments. A distant icy moon is cold because the material making up the moon has little heat and receives little energy. A molecular cloud is cold because the environment within that volume is shielded, sparse, and able to cool. A pre-planetary nebula can become cold because expanding gas over a large region is actively losing thermal energy. These are three different stories wearing the same adjective. This is also where the scale of the universe begins to feel a little more honest. Human imagination tends to favor solid things because solid things are what we know. But much of the cosmos is not arranged as solid things. It is arranged as gas, dust, plasma, radiation, and almost empty space. So if we want to understand the true scale of the universe's coldest regions, we have to stop expecting the answer to look like a frozen planet and allow it to look like a cloud, a halo, a shell, or a dark volume with no surface at all. And perhaps that is part of what makes the subject so calming. These cold regions do not rush. They drift. They stretch. They linger. Their physics unfolds on timescales so long that human urgency has no place in them. In a world full of clocks and deadlines, there is something soothing about turning our attention toward places where motion slows, where heat fades, and where change can take thousands or millions of years. If you are enjoying this quiet descent into the structure of cosmic cold, you can gently support the channel by liking the video, subscribing for more slow explorations like this, and leaving a comment about which feels more haunting to you, a frozen object with a real surface, or a vast cold region with no clear edge at all. Because now the path ahead becomes clearer. We know the universe is broadly cold. We know cold can belong either to objects or to regions. The next step is to bring the story a little closer again and look at the coldest places we can find within our own cosmic neighborhood. Not across the galaxy yet, but nearer home. The quiet shadows, icy traps, and dim worlds of the solar system, where cold first begins to feel tangible enough to picture, and where some of the strangest contrasts in temperature can exist side by side on the very same world. And that is where the scale starts to grow in a way the mind can follow. From a crater in permanent darkness, to a frozen moon, to a world at the edge of sunlight, and then beyond them, into clouds and nebulae and regions so vast that the distinction between place and process begins to blur. But before we go that far, it is worth holding on to this one steady idea. Not every cold thing in the universe is a thing at all. Some are bodies. Some are environments. Some are temporary structures built by motion. Some are long-lived shadows. Some are quiet nurseries for future stars. Some are the fading breath of dying ones. And in that difference lies the beginning of a more truthful picture of the cold universe, one that is far less simple than the old idea of space as one giant freezer, and much more beautiful. So as we drift onward, keep that distinction close. A cold object gives the mind somewhere to stand. A cold region gives the mind somewhere to float. And the universe, as it turns out, contains both in extraordinary abundance. Part 4. The coldest places in our own solar system. Before we drift farther into the galaxy, it helps to stay close to home for a little while. The solar system may feel familiar to us, almost domestic by cosmic standards, but it holds some remarkably cold places of its own. And there is something useful about starting here, because the cold of our local neighborhood is easier to picture. It has shape. It has landscapes. It belongs to worlds we can name. The deeper universe can be difficult to imagine all at once. But a crater on the Moon, a frozen plain on Pluto, a distant moon orbiting Neptune, those places feel just close enough for the mind to rest on them. They give cosmic cold a face. They turn an abstract number into a location, a shadow, a surface, a horizon under a black sky. And what is especially beautiful about the solar system is that it teaches us the first great lesson of cosmic temperature in a way that feels almost personal. Cold is not simply about being far away. Cold is about light, shadow, time, motion, and the way a world holds or loses energy. Some places are cold because they are distant. Some are cold because they are hidden. Some are cold because they have no atmosphere to keep warmth from escaping. Some are colder than we expect, and others are warmer, for reasons that seem almost unfair until physics quietly explains them. So let us move outward slowly, beginning not at the edge, but with the worlds nearest to us. The Moon is a natural first stop. It circles Earth so faithfully that it can start to feel familiar, almost ordinary. But the Moon is a place of violent thermal contrast. In sunlight, its surface can become intensely hot, because there is no real atmosphere to soften the sun's radiation or distribute heat across the landscape. But when the sun goes down, lunar temperatures plunge. Heat radiates away into space, and there is little to hold it back. On most of the Moon, this creates a rhythm of scorching brightness and brutal cold, a cycle tied to its long lunar day and equally long lunar night. Yet the truly cold places are not simply the ones in darkness for a while. They are the places in darkness almost forever. Near the Moon's poles are deep craters whose floors barely, or perhaps never, see direct sunlight. Because of the Moon's slight axial tilt, the sun remains low on the horizon there, skimming the edges of crater rims without ever fully reaching the deepest interiors. These are called permanently shadowed regions, and they are among the coldest places known in the solar system. Some of them may fall to around 25 Kelvin, or even a little below that in the most protected spots. That is colder than Pluto's average surface. Colder than many people would ever expect to find so near Earth. There is something quietly haunting about that. Just a few days' travel away by human standards, there may be pockets of ancient shadow where sunlight has not touched the ground for perhaps billions of years. Places where water molecules, delivered by comets or solar wind chemistry, can remain locked as ice because the cold is so steady and so deep. It is one of the gentlest paradoxes in planetary science. The Moon, which glows so brightly in our night sky, also hides pits of almost permanent darkness cold enough to preserve some of the oldest frozen records in our neighborhood. And the Moon is not alone in this kind of contradiction. Mercury, the innermost planet, seems at first like the last place one should look for cold. It orbits close to the Sun, bathing in intense solar radiation. Its sunlit surface can become hotter than an oven, more than hot enough to melt lead. If you only knew Mercury by reputation, you would think of heat, glare, and bare rock. And yet near its poles, much like the Moon, Mercury also contains permanently shadowed craters. In these hidden places, Temperatures can remain low enough for water ice to survive. This surprises people the first time they hear it. Ice on Mercury sounds almost like a mistake, but it is not a mistake. It is another reminder that temperature is not distributed evenly simply because a planet is near a star. A crater that never sees sunlight can become a cold trap. The rest of the planet may blaze, but the geometry of the landscape writes a different story in the shadows. In some sense, the coldest places in the inner solar system are not found on distant worlds at all, but in carefully hidden corners of worlds we otherwise think of as bright and exposed. Already, the solar system is teaching us something subtle. Extreme cold does not always belong to the edge. Sometimes it belongs to shelter. Mars offers a quieter version of this lesson. It is not one of the coldest places overall, but it is still a deeply cold world by human standards, especially at night and near the poles. Its thin atmosphere is not thick enough to hold warmth well, so temperatures can fall sharply after sunset. Polar winters on Mars are severe, with carbon dioxide itself freezing out onto the surface in seasonal caps. Mars is not cold in the same record-breaking way as the Moon's shadowed craters or the outer icy worlds, but it reminds us that once you leave Earth, warmth becomes fragile very quickly. A world can still have weather, dust, seasons, and sunlight, and yet be far colder than anything most human lives are built to endure. Beyond Mars, the Sun begins to weaken in a way that changes the emotional tone of the solar system. It is still the same star, still pouring out enormous energy, but distance reshapes its power. The asteroid belt lies in this middle region, and though individual asteroids vary, many are cold, dark bodies that absorb little light and spend their lives in an environment far less warm than the inner planets. Farther out, the giant planets wait, and around them, some of the coldest and most intriguing moons in the solar system. Jupiter and Saturn are not themselves where we find the deepest cold, at least not in the simple surface sense, because they still sit in regions where sunlight and internal heat matter significantly. Their upper atmospheres are frigid by earthly standards, of course, but these planets radiate internal heat as well. They are not passive stones cooling in darkness. They are dynamic worlds with atmospheric motion, pressure layers, and internal energy still leaking outward from their formation and contraction. Cold there is complex. But their moons begin to widen the picture. Europa, Ganymede, Callisto, Enceladus, Titan. These worlds are cold, icy, and dimly lit compared with Earth. Their surfaces can sit well below the freezing point of water, some coated in water ice, some mixed with hydrocarbons or more exotic frozen materials. Yet even here, some of the most compelling worlds are not simply dead with cold. Europa may hide an ocean beneath its shell. Enceladus sprays water-rich plumes into space. Titan has a thick atmosphere and methane weather. Once again, the solar system resists the simple equation of cold with lifeless stillness. Some cold worlds remain active. Some may even conceal the ingredients for chemistry far more interesting than their frozen surfaces first suggest. As we continue outward, the emotional quality of sunlight changes again. At Uranus and Neptune, the sun is no longer a commanding blaze in the sky. It is a distant star-like disk, still unmistakable, but stripped of the warmth and dominance it has in the inner worlds. Here, the solar system begins to feel truly remote. And this is where one of the most surprising temperature facts appears. Neptune is farther from the Sun than Uranus, and so common intuition might assume Neptune must be colder. But Uranus is, in a broad atmospheric sense, the colder of the two giant planets. Its upper atmosphere can dip to around 49 Kelvin, making it the coldest planetary atmosphere in the solar system. This is one of those beautiful scientific details that sounds almost mischievous. The farther world is not the colder one. Neptune gives off more internal heat than Uranus does, and that extra energy matters. So once again, distance alone is not the whole story. Cold is shaped not only by how much energy arrives from outside, but by how much escapes from within. There is a calm lesson hidden here. Worlds carry memory. They remember formation, impacts, internal chemistry, buried heat, tilted axes, and the strange histories that make one planet different from another. Uranus does not simply sit farther in one neat ladder of temperature. It has its own character, its own thermal biography. Then come the outermost familiar worlds, the dwarf planets and icy bodies of the Kuiper belt. Pluto is perhaps the most famous, and for good reason. It has become, in the public imagination, a symbol of distance and cold. Its surface temperature is roughly around 40 Kelvin, give or take depending on season and location. That is unimaginably cold by everyday standards. Nitrogen, methane, and carbon monoxide can freeze there. Water ice behaves less like snow and more like rock. The sunlight at Pluto is so faint that noon there can feel dim compared with a cloudy day on Earth. And yet Pluto is not just a frozen relic. The New Horizons flyby revealed a world with astonishing subtlety. Nitrogen plains, water ice mountains, hazes in the atmosphere, signs of seasonal transport of volatiles. Even in the deep cold, Pluto is not a simple dead sphere. It has structure, movement, texture. It changes. It breathes, in its own distant way. Triton, Neptune's large moon, is another wonderfully cold place. Its surface temperature is around 38 Kelvin, making it one of the coldest measured surfaces in the solar system. Triton is especially striking because it seems to be a captured Kuiper belt object, a world that did not originally belong to Neptune but was later taken by its gravity. Its surface is bright, frozen, and strange. It even shows signs of cryovolcanism, where volatiles like nitrogen or other ices can behave in ways that loosely echo volcanism on warmer worlds. Again, the pattern returns. Extreme cold does not mean complete inactivity. The universe is rarely that simple. And then, beyond Pluto, beyond Triton's story, there are countless smaller bodies, dwarf planets, icy fragments, long-period comets, and dark rocks drifting in regions where sunlight is reduced to a pale, patient drizzle. These bodies can be extraordinarily cold, especially if they rotate slowly, reflect much of the light they receive, or spend long ages far from any significant heat source. A comet in the deep outer system is a kind of frozen time capsule, preserving ancient material from the early solar system in a state of profound cold. Some of the coldest objects near us may be these uncelebrated wanderers, unnamed by most people, turning quietly in the dark. But there is another kind of cold in the solar system that deserves attention. Not the cold of distant worlds, but the cold of surfaces turned away from energy. Even a spacecraft can teach this lesson. In deep space, a surface facing the sun may warm significantly, while one turned away can become far colder. Temperature in space is directional. Exposure matters. This is part of what makes the idea of the temperature of space so slippery. A world, a moon, a crater, a panel, a boulder, all of them live in a thermal conversation with radiation, and that conversation depends on what can be seen, what can be blocked, and what can be held. On Earth, air softens these differences. Ocean currents move heat. Winds redistribute it. Clouds reflect and trap energy. The atmosphere acts like a great mediator, smoothing the extremes that would otherwise dominate the surface. Without that mediator, the solar system becomes a harsher place. Sunlit and shadowed become different worlds. Day and night become different climates. A crater becomes a vault. A plain becomes a freezer after sunset. Thermal contrasts sharpen into something almost architectural. So when we ask where the coldest places in the solar system are, the answer depends on what exactly we mean. If we mean the coldest sheltered locations, then permanently shadowed craters on the Moon and Mercury are astonishing contenders, despite their relative proximity to the Sun. If we mean the coldest broad planetary atmosphere, Uranus quietly takes the crown. If we mean among the coldest known surfaces, Triton and Pluto enter the conversation. If we mean small drifting bodies in the outer darkness, countless icy fragments may rival them. And if we mean something more emotional, the places where the mind feels the sun's fading most strongly, then perhaps the edge of the solar system itself becomes the coldest place of all, not just by number, but by mood. This is the first time in our journey that the scale of cold starts to feel familiar enough to hold and strange enough to unsettle. The solar system gives us worlds of shadow and ice, but also contrast. Heat beside cold, ice beside sunlight, frozen places hidden inside bright ones. It teaches us that cold is not a single ladder from warm to cold as you travel outward. It is a map written by angle, material, atmosphere, reflection, internal heat, and time. And beneath all of it lingers the deeper cosmic truth we explored earlier. Even here, even in our local neighborhood, nothing cools in isolation from the wider universe. Every world radiates into a background that is already only a few degrees above absolute zero. The moon's craters are cold not just because they are shadowed, but because what they face beyond that shadow is deep space itself. Pluto is cold not just because it is distant, but because the faint sunlight out there is competing with a universe whose baseline is already almost frozen. There is a tenderness in that idea. The coldest places in our own solar system are like little rehearsals for the larger cosmos. They are local previews of a much grander stillness. Shadows teach it. Distance deepens it. Thin air fails to resist it. And the farther we go, the more the solar system begins to hand us over to the galaxy. If these quiet journeys through the hidden structure of the universe are helping you settle in for sleep, you can gently support the channel by liking the video, subscribing, and leaving a comment about which local cold feels most surprising to you: the moon's dark craters, hidden ice on Mercury, Uranus's atmosphere, or distant frozen worlds like Pluto and Triton. Because from here, the next step is where the scale truly begins to open. So far, we have stayed among objects, moons, planets, craters, bodies with names and surfaces. But beyond the solar system, cold becomes less tied to solid ground and more tied to environment. We leave behind the comfort of worlds and move into the thin darkness between stars, where giant clouds drift, where light is weak, where whole regions can become colder than any familiar landscape. The solar system has shown us that cold can hide in shadow and deepen with distance. Interstellar space will show us something larger. It will show us that some of the coldest places are not worlds at all. And once that shift happens, the imagination has to change with it. No more standing on frozen plains. No more crater rims. No more icy mountains under dim sunlight. Instead, there will be clouds with no surface, darkness with structure, and cold stretched across distances so wide that even the outer planets begin to feel intimate by comparison. But before we leave, it is worth holding onto the strange beauty of what is already here. In our own solar system, just beyond the warmth of home, there are pockets of permanent night. There are worlds where sunlight is too weak to matter much. There are atmospheres colder than instinct expects. There are frozen landscapes under black skies where the stars would shine with a clarity almost too sharp to bear. And all of it exists within one small family of worlds circling one ordinary star. Which means the deeper cold beyond them is waiting with a scale the mind is only just beginning to prepare for. Part 5: The Strange Cold of Interstellar Space. Once we leave the solar system behind, something changes in the imagination. Up to this point, the cold has still belonged to places that feel almost familiar. Craters, moons, planets. Even if they are unimaginably far or unimaginably frozen, they are still worlds. They have surfaces. They give the mind somewhere to land. We can picture a horizon. We can imagine shadows on rock, frost on plains, sunlight falling weakly across ice. But interstellar space is different. Between the stars, the universe begins to lose its edges. The cold is no longer tied so neatly to a world with a name. It belongs instead to a vastness, to regions, to distances, to darkness stretched so far that the solar system itself begins to feel small and sheltered, almost like a warm house we did not realize we were living inside until we stepped outside its door. And that is really what leaving the solar system is like, at least in a thermal sense. It is like leaving the last familiar room of warmth and stepping into the open structure of the galaxy, where the true background character of the universe becomes much harder to ignore. Our sun, for all its ordinary status among stars, dominates everything nearby. Its light defines the orbits of planets, the brightness of days, the temperature of worlds, and even the chemistry of surfaces and atmospheres. As long as you remain within the sun's close influence, the universe still feels organized around a center. Energy is arriving from somewhere obvious. Warmth has a source you can point to. But as you move outward, farther and farther from that source, the sun shrinks. It becomes less of an environment and more of an object. Then it becomes a bright star among other bright stars. And eventually, what you are left with is not the feeling of orbiting home, but the feeling of drifting through a much larger and much colder medium. That medium is interstellar space. The phrase itself sounds emptier than it really is. Interstellar space is often described as the space between stars, and that is true, but it should not be imagined as a clean and absolute void. It is not a perfect nothing. It contains gas, dust, magnetic fields, high-energy particles, and the faint thermal memory of the Big Bang itself. It is sparse beyond ordinary comprehension, but it is not blank. It is more like a nearly empty ocean, with traces of matter spread so thinly that human intuition struggles to hold onto the idea. In the air around you right now, there are countless trillions upon trillions of molecules bouncing into one another constantly. Even in a room that feels still, matter is crowded. Temperature on Earth is social. Molecules touch, collide, share energy, and pass warmth around almost instantly compared with cosmic timescales. Interstellar space is the opposite of crowded. In a typical region between stars, there may be only a few atoms per cc, sometimes fewer. In some denser clouds, that number rises. In some emptier regions, it falls dramatically. But even the denser parts are still extraordinarily diffuse by earthly standards. If you could gather a large jar of interstellar gas and somehow bring it home without changing it, it would feel like almost nothing at all. You would not see thick fog or swirling vapor. You would barely have anything to notice. And yet that almost nothingness has a temperature. It has chemistry. It has history. This is where interstellar cold starts to feel strange. When most people imagine cold, they imagine a substance that can steal heat away. Ice on skin, winter air against the face, cold water around the body. But in interstellar space, there is so little matter that the usual mechanisms of heat exchange become weak and slow. A person floating there would not instantly freeze the way fiction often suggests. There is too little nearby material to pull warmth out of a body by direct contact. Instead, heat would mostly leave by radiation, by slowly shining away into the darkness as infrared energy. So interstellar space is cold, but not cold in the way a freezer is cold. It is not aggressively reaching out to take heat from you. It is simply not giving any back. That difference matters, because it reveals a deeper truth about the cosmos. The cold of deep space is not always a forceful attack. Sometimes it is an absence of rescue, a lack of return, a place where warmth, once lost, has very little chance of being replaced unless a nearby star, shockwave, or other source of energy steps in. And because the distances between stars are so large, this quiet lack becomes the default. The nearest star to our Sun, Proxima Centauri, is more than 4 light-years away. Light, traveling at nearly 300,000 kilometers per second, takes over 4 years to cross that distance. That means the empty-looking region between even neighboring stars is not a narrow gap. It is a vast interior of darkness. A huge volume in which starlight grows weak, matter becomes sparse, and the universe settles into its deeper thermal mood. Still, interstellar space is not all the same. That is another reason it is so fascinating. There are layers to its cold, and each layer tells a different story. Some parts of interstellar space are relatively diffuse and exposed. They are threaded by faint starlight, cosmic rays, and background radiation. These regions may not reach the deepest low temperatures possible because energy still finds ways to move through them. Elsewhere, the gas and dust become denser, enough to block outside light and create darker interiors. In these shielded places, temperatures can fall much lower. It is almost as if the galaxy contains its own weather of darkness, with some regions open and lightly warmed, and others hidden and able to cool more deeply. This brings us to one of the most beautiful structures in astronomy, the molecular cloud. A molecular cloud is a giant region of gas and dust where temperatures are low enough for molecules, not just isolated atoms, to survive in significant numbers. Hydrogen, carbon monoxide, ammonia, formaldehyde, water in icy forms on dust grains, and more complex molecules can all exist there. These clouds are among the coldest large structures in the Milky Way. Many sit at around 10 Kelvin, sometimes a little more, sometimes lower in especially dense cores. 10 Kelvin. It is such a small number that it almost disappears when spoken aloud. 10 degrees above absolute zero. Only about 7 degrees warmer than the cosmic microwave background itself. In everyday life, numbers that close together would barely matter. In the deep universe, they define an extraordinary environment. And yet these clouds are not tiny. Some molecular clouds stretch across dozens of light years, some across hundreds. Inside them, material drifts in darkness so deep that visible starlight can barely penetrate. Dust grains absorb and scatter outside light, helping the cloud cool further. Radiation from stars is muted. The gas moves slowly. Gravity, over immense periods, begins to gather parts of the cloud inward. So here, in one of the coldest environments in the galaxy, something surprising happens. Stars are born. This is one of those ideas that feels almost like a whisper from the universe, one of those quiet reversals that seems too elegant to be accidental. The same cold that makes these clouds dark and still also helps prepare them for collapse. Because the gas is cold, its internal pressure is lower. Because the pressure is lower, gravity has an easier time pulling parts of the cloud inward. Eventually, dense knots can form. Those knots keep collapsing. Temperatures rise in their centers. And one day, a new star ignites. So interstellar cold is not only an ending, it is often a beginning. It is easy to think of cold as a dead state, a final stillness, a kind of cosmic silence after the interesting things are over. But the galaxy does not use cold that way. In many places, cold is a nursery condition, a preparation, a long, patient gathering of possibility. The dark clouds between the stars are not empty waiting rooms. They are workshops, slow and hidden, where the raw material of future suns and planets is held in conditions delicate enough for structure to emerge. There is something deeply calming about that. In human life, we often associate growth with heat, speed, urgency, and visible activity. But the galaxy suggests another model. Some creations begin in the dark. Some futures are assembled in cold silence. Some of the most important places in the universe look, at first glance, like almost nothing at all. If you could drift inside one of these giant clouds, the experience would be difficult even to describe. It would not look like the bright, colorful nebula photographs people often know from books and screens. Those images are usually shaped by special filters, long exposures, and emissions from energized gas. Inside many cold interstellar clouds, especially the darkest ones, there would be very little to see with human eyes. The cloud would be dim, perhaps almost black, because it is defined partly by what it blocks. The stars behind it would disappear. The space around you would feel less like glowing mist and more like an absence layered on top of darkness itself. And yet, unseen in that darkness, chemistry would be happening. Simple molecules would collide gently. Dust grains would gather thin icy coatings. Carbon chemistry would unfold. Radiation from distant stars and cosmic rays would occasionally trigger new reactions. Over immense spans of time, tiny ingredients would build into more complicated forms. It is possible that some of the preconditions for life's chemistry, or at least some of the molecular complexity life later depends on, are helped along in exactly these quiet, cold places. So the interstellar medium is not merely space between meaningful objects. It is meaningful in its own right. This is one of the biggest shifts the mind has to make when thinking cosmically. On Earth, the interesting things usually seem to be the objects. The mountain, the ocean, the city, the tree. Empty space between them feels secondary. But in astronomy, the between can be an active participant in the story. The region between stars shapes how stars are born, how starlight travels, how chemistry unfolds, how shockwaves spread, how dust survives, and how galaxies evolve over time. And because so much of that medium is cold, the cold itself becomes part of the architecture of the Milky Way. There are other interstellar regions, too, that reveal different versions of the same strange chill. Some nebulae are formed not by star birth but by star death. A star nearing the end of its life may shed its outer layers, sending gas outward into surrounding space. Depending on how that gas expands and how much energy it keeps or loses, different temperature structures can emerge. Some are warmer. Some cool dramatically. The Boomerang Nebula is the most famous extreme example, but it belongs to a wider family of interstellar stories in which motion, expansion, and darkness combine to create cold environments. Then there are dark nebulae, thick enough with dust to blot out the stars behind them. These are not necessarily the absolute coldest in every local measurement, but they embody the emotional feel of interstellar cold better than almost anything else. They look like holes in the sky, not because there is nothing there, but because there is enough cold material there to hide the light beyond. The darkness is presence, not absence. The shadow has substance. This is one of the reasons the galaxy feels so mysterious at night. Even when we see the stars, we are also seeing where stars are being hidden. We are seeing regions where matter has become dense enough, and cold enough, to rewrite the view. Of course, interstellar space is not always cold in a simple way. Some regions between stars are heated by nearby stars, by supernova shocks, or by energetic radiation. Some gas can be surprisingly hot and thin. This is part of what makes the interstellar medium such a rich and living system. It contains warm regions, ionized regions, shocked regions, turbulent regions, and cold dense regions all braided together across the galaxy. But if we are asking about the strange cold of interstellar space, what makes it strange is not only the number on a thermometer. It is the scale at which low temperatures can exist without needing a planet or a surface. Entire clouds can remain near 10 Kelvin. Entire regions can stay dark and shielded for millions of years. The place that is cold may be so huge that our solar system could pass through it and still remain only a tiny feature inside. And this is where perspective starts to shift again. Back in the solar system, cold could still be imagined as a local condition on a world. A crater here, an icy plain there. Even Pluto, for all its distance, is still a body with a diameter the mind can eventually write down. But a molecular cloud can be tens or hundreds of light years wide. Its cold is not the temperature of a globe. It is the temperature of an environment so large that stars may be born in one part while other regions remain dark and undisturbed. The cold is no longer scenic. It is structural. It shapes what the galaxy is doing. There is also a soft loneliness to interstellar cold that feels different from the cold of planets. A frozen moon still has a parent planet, perhaps a distant sun in its sky, a history written on a surface. But interstellar clouds and dark regions feel more untethered. They drift between the brighter things. They are not the lanterns. They are the surrounding hush. And yet without that hush, the lanterns would not come into being in the same way. This makes interstellar cold both humble and essential. It does not announce itself with the theatrical force of a supernova. It does not dominate a sky the way a planet or star does. But it prepares, preserves, and shapes. It is the galaxy's quiet labor. If these slow journeys through the hidden architecture of the universe are helping you settle deeper into rest, you can gently support the channel by liking the video, subscribing, and leaving a comment about which idea feels stranger to you. That space can be cold without really touching you, or that some of the coldest regions are also the places where future stars begin. And from here, the next step feels almost inevitable. Once we understand that interstellar cold belongs not just to isolated objects but to giant clouds and environments, a bigger question begins to rise. How large are these cold places really? Not just in poetic terms, but in actual scale. How does a dark molecular cloud compare with the solar system? With the distance to nearby stars? With the larger shape of the Milky Way? Because this is where the universe starts to become difficult in the most beautiful way. The cold is no longer simply extreme. It is enormous. Some of these clouds are so large that if our solar system were placed inside them, it would vanish into insignificance. The orbit of Neptune would become microscopic by comparison. Even the vast Oort cloud, that distant shell of icy bodies surrounding our solar system, would still occupy only a small portion of some interstellar structures. A place can be cold enough for molecules to drift at near minimal energy, yet also large enough to contain the raw material for entire generations of stars. That is not the kind of cold the human mind expects. We are used to associating extreme conditions with small, dramatic things. A frozen drop, a bright spark, a tiny lab chamber. But the universe likes to scale its extremes in ways that are almost gentle. It can create a region colder than anything on Earth and then stretch it across distances that light itself takes decades or centuries to cross. So as we drift onward, hold on to that image. Not a frozen planet. Not a crater. Not even a lonely comet. Imagine instead a dark, cold cloud floating between the stars, almost invisible except where it erases the light behind it, full of slow chemistry, future suns, and matter so calm that it sits only a few degrees above the oldest glow in the universe. Interstellar space is strange not because it is empty, but because it is barely full enough to matter, and yet still full enough to create. It is strange because its cold is not the cold of something dead, but of something waiting. And in that waiting, in that enormous stillness between the stars, the scale of the universe's coldest regions begins to reveal itself in earnest. Part 6. How large the coldest nebulae and molecular clouds really are. Once the mind accepts that some of the coldest places in the universe are not planets or moons, but clouds and regions drifting between the stars, the next question arrives almost automatically. How big are they? Not big in the casual way we use the word on Earth. Not big like a city, or a mountain range, or even a planet. Cosmic big is a different language entirely. It asks the mind to give up familiar scale and begin again. And this is exactly where the cold universe becomes especially difficult, and especially beautiful, to picture. A frozen world, no matter how distant, still gives us something human-sized to imagine. It has a diameter. It has a surface. It has a shape we can eventually sketch. But a molecular cloud, a dark nebula, or a cold star-forming region does not fit so neatly inside the imagination. It is not a globe hanging in space. It is a volume, a drifting architecture of gas and dust, a structure so spread out that calling it a cloud can almost be misleading, because the word sounds soft and local, while the real thing can stretch across distances that swallow entire solar systems without noticing. This is where cosmic cold stops feeling merely extreme and starts feeling immense. If the coldest crater on the Moon teaches us what local cold looks like, then a giant molecular cloud teaches us what large-scale cold looks like. And the difference between those two is almost impossible to overstate. A crater might be a few kilometers or tens of kilometers across. A cold molecular cloud can span dozens, sometimes hundreds of light years. A light year, of course, is the distance light travels in 1 year. About 9.46 trillion kilometers. Nearly 5.88 trillion miles. That number is so large that it does not really behave like an ordinary number anymore. It behaves more like a signal that ordinary intuition has reached its limit. So let us slow it down. Imagine the orbit of Earth around the Sun. That already feels large in human terms. Now imagine the orbit of Neptune, far out in the dark, around 30 times farther from the Sun than Earth is. The solar system begins to feel broad there, stretched and remote. But if you place that entire planetary system inside a typical cold interstellar cloud, it barely registers. It becomes a tiny little arrangement, almost microscopic against the cloud's total width. And even that can still be an understatement. Some of the giant molecular clouds in our galaxy are not merely a little larger than the solar system. They are incomprehensibly larger. The Orion Molecular Cloud Complex, associated with the Orion Nebula and the great dark lanes around it, stretches across hundreds of light years. The Taurus Molecular Cloud is smaller, but still vast beyond normal comprehension, spread across roughly 30 light years or more. The Pipe Nebula, the California Nebula region, the Rosette Molecular Cloud, the Eagle Nebula's larger environment. These are not little puffs in space. They are major structures in the Milky Way. Entire stellar neighborhoods are born from them. To really feel that scale, it helps to abandon the numbers for a moment and compare them to what we already know. If our solar system out to Neptune were reduced to the size of a coin, many cold molecular clouds would still be so large by comparison that the nearest similar coin might be placed across a continent, not across a room. And that still would not fully capture the emptiness within them. Because these clouds are huge, yes, but they are also thin. Their largeness is not the compact largeness of a mountain. It is the spread out largeness of fog over a valley, except the valley is measured in light years and the fog can one day turn into suns. This is one of the strangest things about the universe. It can build structures of enormous size out of matter so diffuse that, if you gathered a piece of one into your hands, you would feel almost nothing at all. A cold molecular cloud is not dense in the way people usually imagine. On Earth, clouds are made of droplets in air that we can walk through. Cosmic clouds are different. They are much thinner than the best vacuums most people have ever heard of. And yet because they are so enormous, because they stretch across such great distances, the total amount of material inside them can still be vast enough to form thousands, even tens of thousands, of stars. That is the scale we are dealing with now. Not the scale of a place you could cross in a day, or a year, or in a human lifetime. The scale of a region where light itself needs decades or centuries just to move from one side to another. There is something very calming about that, once the mind stops resisting it. A place this large cannot be rushed. Nothing about it is urgent. Its chemistry unfolds slowly. Its collapses happen over immense spans of time. Gravity works in silence there, with no need to hurry. The cloud does not care whether a civilization rises or falls on one small planet around one ordinary star. It keeps drifting, cooling, shielding, gathering, and preparing the next generation of stars on timescales so deep that human history is barely a blink. And the cold is part of what makes the largeness meaningful. If these clouds were hot throughout, their internal pressure would resist collapse more strongly. They would not so easily fragment into denser pockets. But because they are cold, Often only around 10 Kelvin or so, the gas moves more slowly. The pressure is gentler. Gravity can begin to shape the cloud from within. Not all at once, and not everywhere, but in certain places where matter becomes slightly denser than average. Over time, those places gather more matter. They sink inward. They form cores. And inside those cores, new stars may one day ignite. So when we ask how large the coldest nebulae and molecular clouds really are, the answer is not just a matter of measurement. Their size is part of their function. Their scale allows them to become reservoirs, nurseries, and dark storehouses of possibility. Take the Orion region, for example. Many people know Orion as a bright winter constellation, easy to spot, with its famous belt and sword. But the visible stars are only the surface of the story. Behind and around them lies a much larger structure of gas and dust. The Orion molecular cloud complex stretches across hundreds of light years and contains some of the nearest large star-forming regions to Earth. Inside that dark, cold structure, stars are forming at different stages. Some are already glowing. Some are still buried. Some may not form for a very long time yet. Now pause and really consider what that means. The familiar pattern of Orion that people have looked at for thousands of years is embedded in a cold structure so vast that our entire species has only just begun to understand its true size. The stars people used for navigation, for mythology, for stories told by firelight, are part of a much bigger dark architecture that was there long before any human eye looked up. And Orion is only one example. The Milky Way is threaded with giant clouds like this, long dark lanes crossing spiral arms, cold reservoirs tucked inside the galaxy's broader glow. If you could step far outside the Milky Way and look back with the right kind of vision, you would not just see stars. You would see a galaxy whose luminous beauty is braided with cold matter, hidden matter, future matter. Some of its most important structures would appear not as bright ornaments but as dark and quiet masses, places where light is blocked and where the next chapter of the galaxy is slowly being written. There are even larger structures known as giant molecular clouds, and then larger still, associations and complexes, where multiple cold clouds, star-forming knots, and dust lanes belong to the same wider environment. These can extend across hundreds of light years. In some cases, the scale becomes so broad that one cloud system can influence the birth of many different stellar groups over time. A supernova may shock one side of a cloud. Radiation from a new cluster may erode another side. Dense pockets may collapse here while other regions remain still and dark. The cloud becomes less like one single object and more like a weather system spread across part of the galaxy. This is where the word region becomes especially important again. We are no longer talking about a thing with a neat edge, like a cold moon. We are talking about environments with texture, layers, density gradients, filaments, cavities, knots, and flows. Some parts are denser. Some are more protected from outside starlight. Some are warmer from nearby star formation. Some are so cold and dark that they almost vanish except where they blot out the stars behind them. And because of that, scale in these places is not always simple to define. How big is the cloud? That depends, in part, on what density threshold you choose. How dark does the gas have to be before you count it as part of the main structure? How thin can it become before you say the cloud has ended? Even the edges are soft. Cosmic structures often fade rather than stop. That softness of boundary makes the cold feel even more dreamlike. A crater has a rim. A planet has a limb. But a molecular cloud often becomes thinner gradually, merging into surrounding space. You do not always arrive at a wall and say, "Here it ends." Instead, the cloud trails off, parting slowly into the wider interstellar medium. The cold does not simply stop. It eases away. There is also another scale hidden inside these clouds, a smaller scale nested inside the giant one: dense cores. Within a giant cold molecular cloud, certain parts become denser than the rest. These cores may be only fractions of a light year across, perhaps a few thousand astronomical units to a few tenths of a light year. Compared with the whole cloud, they are tiny. But compared with the solar system, they are still vast. And inside them, temperatures may remain extremely low while gravity continues its patient inward work. These are the actual cradles of future stars. So now the structure becomes layered in a beautiful way. A giant cold cloud stretches across tens or hundreds of light years. Inside it sit filaments and knots. Inside those lie dense cores. Inside some of those, a protostar begins to form. Then, eventually, fusion ignites, and a new local source of heat and light is born inside a much larger sea of cold. Warmth emerging from cold. Light emerging from darkness. This happens over and over again in the galaxy. The large cold structure makes the small bright structure possible. If we return to the question of scale, one of the best ways to feel it is to think about travel. Human beings reach the moon in a matter of days. Even missions to the outer planets, though they take years, still move within a region that feels connected to the sun. But to cross a cold molecular cloud tens of light years wide, even light would need tens of years. A spacecraft moving at the speeds humans currently use for interplanetary travel would need timescales so long that they drift beyond practical imagination. The coldest large regions of our galaxy are not merely far away. They are internally enormous. And then there are nebulae associated with stellar death or stellar illumination. Here again, size can surprise us. The bright visible part of a nebula, the part captured in famous images, is often only the easiest part to see. Around it may lie larger shells, halos, or associated cold material invisible in ordinary photographs. The visible beauty is sometimes just the lit edge of a larger, colder structure. This is important for the imagination, because it teaches us not to trust only what glows. The universe often hides its scale in darkness. The bright center may attract our attention, but the larger cold region around it may carry more mass, more volume, and more meaning. A nebula can look like a shining shape floating in space, when in truth it is embedded in, or bordered by, a much larger dark system that stretches far beyond what the eye would guess. That is part of what makes the cold universe feel so profound. Its biggest truths are often dim. If this slow journey through the hidden architecture of cosmic scale is helping you unwind, you can support the channel in the simple way that always helps, by liking the video, subscribing, and leaving a comment about what feels more surprising to you so far, that some of the coldest regions are also star nurseries, or that a single cold cloud can be vastly larger than our entire solar system. There is another way to understand the size of these structures, and it may be the gentlest one of all. Think of weather on Earth. A fog bank rolling over a field. A storm system moving across a country. A jet stream crossing a continent. Now expand that idea into space, remove almost all the density, lower the temperature to just a few degrees above absolute zero, and stretch the whole thing until it spans light years. That is not a perfect comparison, but it points the mind in the right direction. The cold clouds of interstellar space are not isolated pebbles or little islands. They are sprawling conditions. Galactic weather on scales so large that stars are one of the things they produce. And once that clicks, the Milky Way begins to feel less like a collection of isolated stars and more like a living structure with cold veins running through it. Dark lanes in the galaxy. Molecular complexes in its spiral arms. Hidden reservoirs where future light is being assembled. This is not scenery. This is infrastructure. It also helps explain why the question of the true scale of the universe's coldest regions is more interesting than it first appears. We might begin by expecting a contest of temperatures, a simple list of the coldest things. But the deeper truth is that some of the most important cold in the universe is not notable only because of how low the number is. It is notable because of how much space that low temperature can occupy. A temperature of 10 Kelvin spread across a region hundreds of light-years wide tells a much different story than the same temperature on the shaded rock of a distant moon. The number is the same kind of number. The reality is not the same at all. One is local cold. The other is architectural cold. And architecture is really the right word now, because these clouds shape what comes next. Their size determines how much material they can hold. Their density structure determines where stars can form. Their shielding determines how cold their interiors can remain. Their position in the galaxy determines what radiation, pressure, and shockwaves they must endure. A giant cold cloud is not just a passive place where temperature happens to be low. It is a major actor in the long life of a galaxy. So perhaps the calmest way to picture them is this. Imagine drifting far above the Milky Way, looking down not with human eyes, but with a sense broad enough to feel both light and darkness. You would see spiral arms dusted with stars, yes, but you would also see the colder structures woven among them. Dark ribbons, cold reservoirs, quiet regions so large that whole star systems could be born and die within one small corner of them. And much of that structure would not announce itself with brilliance. It would whisper through shadow. That is the true scale we are entering now. The coldest large regions are not little anomalies tucked away in corners of space. They are part of the galaxy's main body. Some are among its biggest and most essential working parts. They stretch across distances too large for the mind to hold all at once, and yet they remain only one level in a still larger cosmic hierarchy. Because soon we will move from the general cold of giant clouds to something even more extreme and specific. A place that seems, at first, impossible. A place where cold does not merely spread across a large region, but drops below what the background universe itself should allow. And when we reach it, the scale we have built here will matter. Because without first understanding how enormous cold structures can already be, it is hard to appreciate just how astonishing one particular object really is. The Boomerang Nebula is waiting ahead, not just as the coldest known natural place, but as proof that a region can become so large, so active, and so thermally unusual that it briefly seems to outrun the universe's own background temperature. But before we go there, it is worth lingering for one more breath in the giant quiet of these cold clouds. The clouds that do not shine very brightly. The clouds that hold future suns in darkness. The clouds that stretch across light years with temperatures only a few degrees above absolute zero. The clouds that remind us the universe is not built only from blazing stars, but also from long cold intervals between them. Those intervals are larger than we first imagined, much larger. And in that immense dark calm, the universe prepares its next lights. Part 7: The Boomerang Nebula and the Coldest Known Natural Place. We have been moving outward in widening circles. From the shadows of the moon, to the frozen worlds of the outer solar system, to the giant dark clouds that drift between the stars, each step has asked the mind to loosen its grip on ordinary scale. Cold, we have learned, is not always a surface. Sometimes it is a region. Sometimes it is a process. Sometimes it is a darkness so large that entire solar systems could vanish inside it. And yet, even after all of that, there is still one place that stands apart. Not because it is the biggest cold structure in the universe. It is not. Not because it is the emptiest. It is not that either. It stands apart because it seems to do something the universe should not casually allow. It becomes colder than the background temperature of space itself. Colder than the old afterglow of the Big Bang that quietly fills the cosmos. It is, at least so far as astronomers know, the coldest known natural place ever found. It lies about 5,000 light-years from Earth in the constellation Centaurus, and it is called the Boomerang Nebula. We met it earlier, almost like a rumor at the edge of the story. A place so cold it felt nearly impossible. But now that we have built the scale around it, now that we have passed through the solar system and the great cold clouds of interstellar space, we can return to it properly. Not as a strange fact to be admired from a distance, but as a real place with a real shape, a real history, and a real lesson to offer about what cold can become when the universe pushes a dying star to an extreme. The first thing to understand is that the Boomerang Nebula is not famous because it sits quietly in darkness for a very long time, like some frozen rock abandoned far from any star. That would make sense to the intuition. But the boomerang is not cold because nothing is happening. It is cold because far too much is happening. That is the paradox at the heart of it. Many cold places in the universe are calm by necessity. They are shielded from starlight, distant from heat, protected by dust, or isolated enough to cool slowly over time. The Boomerang Nebula is different. It is not a place of simple stillness. It is the aftermath of violence. A star near the end of its life is throwing material outward with such speed, and in such quantity, that the expanding gas cools itself to an extraordinary degree. In other words, the cold is not passive. It is engineered by motion. To picture the Boomerang Nebula gently, it helps to forget the word nebula for a moment and think instead of a dying star wrapped in its own escaping breath. At the center is an aging red giant, a star in one of the last dramatic stages of its life. Stars like this do not die all at once. They swell, shed, destabilize, and gradually lose their outer layers. Eventually the core will be left exposed and hot, and the surrounding gas will glow as a planetary nebula. But the Boomerang Nebula is seen slightly earlier than that, in what astronomers call a pre-planetary nebula stage. It is a brief transitional phase, a kind of cosmic in-between, where the star is already losing mass in a spectacular way, but has not yet fully lit its surroundings into the kind of bright planetary nebula people often imagine. There is something almost intimate about that timing. We are not seeing a stable monument. We are catching an event in motion, a short chapter in a much longer stellar life. The Boomerang Nebula is remarkable partly because we happen to see it at just the right moment, while its ultra-cold outflow still exists and before the surrounding gas warms too much. Astronomers note that it is already slowly warming, which means this deep freeze is not permanent. It is a temporary state, a rare and fleeting one. That makes the boomerang feel even more dreamlike. Imagine a place that becomes the coldest known natural object in the cosmos, but only for a short while. A kind of cosmic winter that arrives not over a planet or a moon, but around a dying star. It does not last forever. It is a phase, a narrow window, a deep breath of cold released into the galaxy, and then, slowly, it begins to fade. Its temperature is the detail that first pulls people in. Around 1 Kelvin, roughly minus 272 degrees Celsius, or minus 458 degrees Fahrenheit. Just about 1 degree above absolute zero. Lower than the 725 Kelvin background glow of the universe. Lower than the cosmic microwave background itself. That is what makes it so extraordinary. Deep space already rests at a hauntingly low thermal floor, but the Boomerang Nebula drops beneath it. It does not merely sit inside a cold universe. It briefly undercuts the universe's own baseline. It is worth pausing there. The universe is not easy to surprise. It is large enough to contain black holes, neutron stars, gamma-ray bursts, vast dark matter halos, and galaxies colliding across millions of light years. So when something manages to stand out even against that backdrop, it deserves a slower look. The Boomerang Nebula is not the hottest, brightest, or biggest thing in the sky. It is a subtler marvel. A place that whispers rather than shouts. A place whose record is written not in fire, but in an almost impossible absence of motion. And yet its appearance is strangely theatrical. Seen in visible light, the Boomerang Nebula can look like an hourglass or a ghostly bow tie, a pale bipolar structure floating in darkness. Older observations gave it the name Boomerang because its shape seems slightly curved from Earth-based telescopes. Later Hubble images revealed more of that soft hourglass form. But even that turned out not to be the whole story. ALMA observations showed that what we see in visible light is only part of a larger structure. The bright or pale lobes are not the entire cold region. They are the more visible inner outflow, shaped in part by dust near the center. Beyond them lies a larger, roughly round ultra-cold outflow that does not announce itself so clearly in ordinary optical images. This is such a familiar lesson in astronomy that it almost becomes a philosophy. The visible part is not always the whole thing. What looks elegant and contained from a distance often turns out to be only the lit inner portion of a much broader reality. The Boomerang Nebula is like that, a ghostly hourglass inside a larger sphere of cold, a visible mask draped over a much more expansive thermal event. The inner hourglass-shaped outflow stretches more than 3 trillion kilometers from end to end, about 21,000 times the distance from Earth to the Sun, and according to ALMA's measurements, the ultra-cold outflow surrounding it is more than 10 times larger still. Material at those outermost edges appears to have taken roughly 500 years to travel there after being expelled from the dying star. That means the coldest known natural place is not some tiny freak pocket in a corner of the sky. It is large. Large enough that the visible image most people recognize is only the center of the story. Large enough that the deep cold occupies a region far more expansive than intuition first suggests. It is not on the scale of a planet, not on the scale of a solar system. It belongs to that larger category we have been building toward all along, the category of cold environments and outflows, where scale is measured not in kilometers alone but in light, time, and spread. And now we can see why this matters. Earlier, when we spoke about molecular clouds, the key lesson was that cold can become structural. Entire regions can remain near 10 Kelvin across huge spans of space. The Boomerang Nebula takes that lesson and sharpens it. Here, the cold is not only regional. It is active. It is process-driven cold on a large scale. The outflow is expanding at around 164 kilometers per second, and that rapid expansion is what drives the temperature downward. As the gas rushes outward, it spreads, and in spreading it spends energy. The result is adiabatic cooling on a cosmic scale, the same broad principle that can make expanding gas cool, but here taken to an astonishing astronomical extreme. So if a giant molecular cloud is the quiet long winter of interstellar space, the Boomerang Nebula is something like a sudden and violent cold front produced by a star's own dying breath. That image is not perfect, of course. No earthly weather analogy truly survives this kind of scale. But it points toward the emotional truth of the thing. The boomerang is not merely left in the dark. It is making its own cold through motion, through loss, through a rapid unmaking of itself. There is a deeper sadness to that, and also a kind of beauty. Stars spend most of their lives resisting collapse and loss. They balance gravity with fusion. They hold themselves up through light. But near the end, for some of them, the balance changes. The outer layers become unstable. Matter begins to escape. The star can no longer keep itself in the same form. The Boomerang Nebula is a record of that surrender, but not a quiet one. It is a dramatic shedding, perhaps influenced by a companion star, perhaps by a close binary interaction that helped trigger the unusually fast and massive outflow. ALMA's 2017 release points to the likely role of two interacting stars, suggesting that the only way to eject so much mass at such speed is through the gravitational energy of such an interaction. That possibility makes the nebula feel less like a solitary death and more like a complicated farewell. Not one star simply fading, but a system disturbing itself into one of the strangest cooling events we have ever seen. And there is another reason the Boomerang Nebula matters to this journey. It helps us refine what we mean by coldest. The emptiest spaces between galaxies may feel colder in a poetic sense. The darkest molecular clouds may be cold across much larger regions for much longer periods. The future universe may cool still further on grander scales. But when astronomers say the Boomerang Nebula is the coldest known natural place, they mean something specific. They mean that its gas has been observed to drop below the cosmic microwave background, below the normal background temperature of deep space. That is what gives it its special status. Not simply that it is chilly, but that it becomes colder than the universe's own ambient glow. This distinction is important, because it prevents the mind from flattening all cosmic cold into one idea. The Boomerang Nebula is not the most representative cold place. It is not the most typical. It is an outlier, a record holder, a beautiful exception created by a very particular combination of geometry, stellar evolution, outflow, and time. If molecular clouds show us the galaxy's steady cold infrastructure, the boomerang shows us what can happen when the same universe briefly produces a superlative. And even its name contributes to the feeling. Boomerang. A simple human word applied to a ghostly structure thousands of light years away. The name comes from how it once looked through telescopes, a slight asymmetry, a suggestion of a curved return. It is almost tender how often astronomy does this, placing ordinary language on extraordinary things, as if the mind cannot help trying to bring the universe closer by naming it with familiar shapes. Yet the real structure is stranger than the name. Not a curved toy, but an hourglass nested inside a larger frozen outflow, a star's final act turning itself inside out. If you let the imagination slow down around it, the Boomerang Nebula becomes less like a science fact and more like a scene. A red giant star near the end of its life. Dust gathering around the center. Light leaking out in opposing directions. Gas thrown outward at tremendous speed. The visible lobes stretching across trillions of kilometers. The larger ultra-cold outflow extending much farther still. And all of it suspended in the dark of Centaurus, about 5,000 light-years away, cooling itself below the universe's background whisper while it still can. There is no sound there, of course. No wind in the human sense. No roaring blast anyone could hear. Just motion, dust, radiation, geometry, and time. A cosmic event whose violence is expressed as silence. That may be one of the most quietly moving things about it. The universe often hides its fiercest processes inside places that look calm from a distance. And because this phase is short-lived, it reminds us of another truth we often forget. The sky is not a finished museum. It is a living history of moments caught in different stages. Some stars are being born. Some are stable. Some are dying. Some are surrounded by giant cold clouds. Some are creating them. The Boomerang Nebula feels singular because we happen to catch it during its coldest chapter. If we had arrived too early, it would not yet look the same. Too late, and it would already be warming past the record that now makes it famous. That means the coldest known natural place in the cosmos is also, in a way, a timing miracle. Not a miracle in the supernatural sense. Just the quiet astonishment that comes from seeing the right thing at the right phase with the right instruments. A reminder that astronomy is not only about where things are, but when we happen to find them. If this gentle journey through the strange architecture of cosmic cold is helping you settle in, you can support the channel in the softest possible way, by leaving a like, subscribing, and sharing in the comments which part of the Boomerang Nebula feels most haunting to you. The fact that it is colder than the background of space, or the fact that this cold may only be a brief passing stage in a dying star's life. Because the story does not end here. In some ways, the Boomerang Nebula is the climax of one kind of cold, the cold of a record-breaking natural object created by a powerful local process. But there is another kind of scale still waiting for us. A scale defined less by one dramatic object and more by absence itself. the spaces between stars, the distances between galaxies, the vast quiet between galaxy clusters. Regions that are not colder than the boomerang in the strict measured sense, and yet can feel even more overwhelming because of how much emptiness they contain. That is the next widening of the circle. So before we leave this strange ghost and Centaurus behind, let us hold on to what it has taught us. The coldest known natural place is not a world you could stand on. It is not a giant iceberg drifting at the edge of creation. It is the outflow of a dying star. A temporary structure, a brief geometry of dust and expanding gas, a place where motion creates stillness at the microscopic level, where loss produces chill, and where the universe, for a short and beautiful moment, manages to cool part of itself below its own background glow. It is not the whole story of cosmic cold, but it is one of its most unforgettable chapters. And when we widen out again from this ghostly hourglass to the immense dark spaces beyond, the lesson comes with us. Cold is not only about low numbers. It is about what shape the universe gives that low energy. A crater, a cloud, a shell, a dying star's breath, a vast intergalactic interval. The Boomerang Nebula is one answer. The emptiness beyond it will offer another. Part 8. Cold voids between stars, galaxies, and clusters. After the Boomerang Nebula, it may feel as though we have reached the end of the story. A dying star, a ghostly outflow, a place so cold it slips below the background temperature of the universe itself. It is tempting to stop there, to let that one extraordinary object stand as the final answer to what cosmic cold can be. And in one very important sense, it does. If we are asking for the coldest known natural place ever measured, the Boomerang Nebula remains the great exception, the strange and beautiful record holder. But there is another side to the question, and it may be even more haunting. What about the places that are not colder in the strictest measured sense, but are colder in mood, in scale, in emptiness? What about the vast dark intervals that separate stars from one another, galaxies from one another, and clusters from one another? What about the cold that is not concentrated inside one dramatic object, but stretched across such huge distances that the mind can barely keep hold of it? Because if the Boomerang Nebula teaches us how low temperature can go in one remarkable place, the great voids of the universe teach us something different. They teach us what cold feels like when it becomes distance itself. There is a subtle shift here. Up to now, even the largest cold clouds and nebulae have still felt like structures. They had matter gathered in one region. They had shape, density, outflow, shadow, chemistry. But a void is defined more by what is not there. Not complete nothingness, of course. The universe almost never gives us true nothing, but close enough that the remaining matter becomes sparse beyond ordinary imagination. And that is where the emotional scale of cosmic cold changes again. The space between stars already feels enormous to us. Our own solar system, for all its breadth, is still just a small clearing around one star. Beyond its outermost planets, beyond the Kuiper belt, beyond even the imagined shell of the Oort cloud, the sun's influence thins into the wider galaxy. The nearest star is still more than 4 light-years away. That means the region between even neighboring stars is not a narrow gap. It is a true wilderness of darkness. In that wilderness, warmth becomes rare. Starlight still exists, but weakly. A star may dominate its own immediate surroundings, but the farther you drift from it, the more it shrinks into one light among others. The temperature of isolated matter out there begins to settle toward the wider background of the cosmos. There are still particles, still dust, still traces of gas, still the low glow of the cosmic microwave background. But the feeling is no longer one of orbiting something bright. It is the feeling of crossing an interval. And intervals, in the universe, are often much larger than the things they separate. This is a quietly important truth. We tend to think in terms of objects. Stars, planets, moons, nebulae, galaxies. But the universe may be even more defined by the spaces between those things. Between stars there is darkness. Between galaxies there is more darkness still. Between galaxy clusters, the distances become so vast that even a whole galaxy starts to feel like a small island drifting in a sea that has no shore. So let us move outward gently. First, the gaps between stars. Inside a galaxy like the Milky Way, stars are not packed shoulder to shoulder. They are separated by immense distances. In the denser regions near the galactic center or inside a cluster, the spacing may be somewhat tighter. In regions like our own local stellar neighborhood, stars are scattered with great patience. Each one carries its own small territory of planets, dust, comets, and fading light, but the territory ends quickly compared with the distances beyond it. That means much of a galaxy is not made of stars themselves. It is made of the space between them, and that space is cold. Not aggressively, not like winter wind or icy water, but in the deeper cosmic sense. It is low in density, low in energy, and largely given over to the faint background hum of the universe. There may be gas drifting there, but spread thinly. There may be dust, but not enough to create the kind of dense darkness found in a molecular cloud. There may be starlight passing through, but from very far away. The dominant experience of such a place is not heat. It is distance. It is worth slowing down enough to feel how strange that is. A star can burn for billions of years, flooding nearby space with energy. Planets can circle it. Atmospheres can trap its warmth. Oceans can rise and fall under it. Life, in rare cases, can grow beneath it. But a few light years away, outside that immediate influence, the larger mood of the galaxy reasserts itself. The warmth does not continue smoothly forever. It fades. The darkness between stars is always waiting. And yet even this is only the beginning. Because galaxies themselves are also separated by vast intervals. Our Milky Way is not alone. It belongs to a small group of galaxies, including Andromeda, the Triangulum Galaxy, and dozens of smaller dwarf galaxies. Even within this local group, the distances are immense. The space between the Milky Way and Andromeda is about 2.5 million light-years. That is not the sort of number a human mind can truly inhabit. It is not merely far. It is almost purely conceptual. If light itself needs 2.5 million years to make that crossing, then the interval is already beyond anything that can feel like a journey in the ordinary sense. And what fills that interval? Very little. There is an intergalactic medium, a thin spread of gas, traces of matter, dark matter shaping the gravitational landscape, radiation moving through, and the ever-present background of the CMB. But compared with the bright body of a galaxy, the space between galaxies feels almost naked. There are no nearby suns to dominate the local scene. No planetary systems warming one small patch after another. No dense clouds blocking light in obvious shapes. Just long reaches of low-density matter under the oldest glow in existence. This is where the cold of the universe begins to feel less like an environmental condition and more like a philosophical one. Between galaxies, there is no horizon in the usual sense. No sky shaped by atmosphere. No day. No familiar night either. Just blackness punctuated by remote structures so far away that even entire spiral galaxies can seem like decorative flecks on a much larger backdrop of absence. The cold here is not only temperature. It is separation itself. It is the fact that so much of the universe exists not in the bright interiors of things, but in the impossible distances between them. And yet the deeper we go, the more careful we have to become with the word cold. Because here the universe starts to play one of its favorite tricks on intuition. It turns out that emptier does not always mean colder. This is important. Very important. The space between galaxies can be extremely sparse, but not all of it is at the lowest temperatures we might imagine. Some intergalactic gas has been heated by ultraviolet radiation from galaxies and quasars. Some has been shocked by the motion of matter falling into larger structures. Some resides in filaments of the cosmic web where gravity has stirred and compressed it over time. So although the intergalactic medium often feels like the natural home of deep cold, parts of it can actually be much warmer than simple instinct would suggest. And then there are galaxy clusters. A galaxy cluster is one of the largest gravitationally bound structures in the universe, containing hundreds or even thousands of galaxies held together by gravity. At first glance, one might imagine the space inside a cluster to be dark and freezing, with galaxies separated by cold emptiness. But the truth is stranger. The space between galaxies in a cluster is often filled with incredibly hot, thin gas known as the intracluster medium. This gas can reach temperatures of millions of degrees. Millions. That sounds almost absurd after everything we have been saying about cold. But it is true, and it reveals once again that low density is not the same as low temperature. A region can be incredibly thin and still be very hot if the particles inside it carry high energies. In clusters, gravity, collisions, and the enormous mass of the system can heat the gas dramatically. The particles are sparse by earthly standards, yes, but each one is moving with tremendous energy. So now the story becomes even more beautiful. The great gaps between stars may often be cold in the broad background sense. The larger spaces between galaxies may feel colder still in mood and emptiness. But some of the grandest structures of all, the galaxy clusters, can contain vast seas of very hot gas. The universe refuses simple rankings. Darkness does not automatically mean cold. Emptiness does not guarantee stillness. Scale and temperature are related, but not obedient to the imagination. And yet, beyond these clusters, beyond the filaments and glowing islands of matter, there are still the voids. Cosmic voids are among the largest recognizable structures in the large-scale universe. They are not empty in an absolute sense, but they are much emptier than average. Fewer galaxies, less gas, less matter, less structure. They are the vast underdense regions between the filaments and walls of the cosmic web. Some are tens of millions of light-years across. Some are much larger. These are not little pockets of absence. They are continental-scale gaps in the architecture of the cosmos, except even that comparison is too small by more orders of magnitude than language can comfortably hold. This is where cold becomes almost abstract again. A cosmic void is not a place you could point to in one night sky and say, there it is, like a moon or a nebula. It is a region of the universe defined by low density over unimaginable distances. It may contain a few lonely galaxies, drifting like forgotten boats in an inland sea of darkness. But on the whole, a void is remarkable for what it lacks. Fewer lights, fewer collisions, fewer heating sources, fewer events. And because the universe is expanding, those voids become even emptier over time. That may be one of the most haunting facts in all of cosmology. The universe does not merely contain emptiness. It is making more of it. As cosmic expansion continues, matter on the largest scales becomes more spread out, and underdense regions grow more underdense. The filaments and clusters remain where gravity has gathered things together, but the voids between them widen. The cold, quiet intervals of the universe are not static scenery. They are part of an ongoing transformation. The architecture of large-scale emptiness is deepening. There is a kind of stillness in that idea that almost feels physical. Imagine a region tens of millions of light-years across, containing only a few scattered galaxies and enormous stretches where almost nothing happens. No nearby stars. No dense clouds. No planets warming under a local sun, just ancient radiation, traces of matter, and the slow widening of space itself. It is difficult to know what such a place would feel like, because human feeling evolved in environments full of surfaces, sounds, weather, and life. A cosmic void offers none of that. It offers only scale and silence. And perhaps that is why these regions feel so powerful in the imagination. The Boomerang Nebula astonishes because it is a dramatic exception. A dying star making itself colder than the cosmic background. But a cosmic void astonishes for almost the opposite reason. Not because something extraordinary is happening, but because so little is. It is not a spectacle. It is a withdrawal. A region where matter itself seems to have stepped back, leaving behind a calmer and lonelier geometry. And still, even here, we should be careful. A void is not necessarily colder than the Boomerang Nebula in the strict measured sense. The boomerang remains the colder natural object because its gas drops below the CMB. A void, even if emotionally colder, still lives inside the universe's background radiation. It is bathed in that faint 725 Kelvin afterglow just like everything else. It may be sparse. It may be dark. It may be emptier than almost anywhere else. But the old light of the Big Bang still passes through it. That means the cold of voids is not the record-setting cold of an outlier. It is the background cold of a place with almost nothing left to interrupt it. There is a profound difference between those two kinds of cold. One is a local miracle of process. The other is the large-scale honesty of the universe when structure thins away. And if you let yourself rest with that distinction for a moment, the emotional shape of the cosmos begins to change. You realize that most of reality is not happening where stars burn. Most of reality is not inside galaxies, or on planets, or in those rare little patches where life has time to think about itself. Most of reality is distance. Low-density distance. Ancient background light crossing enormous dark intervals between the bright exceptions. The universe, in its broadest form, is not a crowded cathedral of stars. It is a sparse web suspended over vast reaches of cold silence. That does not make it bleak. Not necessarily. In a strange way, it makes it tender. Because it reminds us how local warmth really is. How precious. How specific. Every star is a little argument against the background. Every living world is a delicate arrangement of retained heat in a universe that, almost everywhere else, has relaxed toward stillness. The deeper the cold voids become in the imagination, the more miraculous even an ordinary sun begins to feel. There is also something deeply sleep-like about these scales. A molecular cloud still contains the promise of future stars. A nebula still carries the drama of outflow and motion, but a void is closer to pure interval. It is the universe exhaling. It is the pause between structures, the long blank measure in the music. If galaxies are the notes, then voids are the silence that makes the notes distinct. And perhaps that is why they feel so immense. Not just because they are large, but because the mind has so little to hold on to inside them. A galaxy gives us shape. A star gives us focus. A planet gives us scenery. A void gives us almost none of those things. It gives us absence over scale. The kind of scale that makes even thought feel small. If these slow journeys through the deep structure of the universe are helping you unwind, you can gently support the channel by leaving a like, subscribing, and sharing in the comments which feels more haunting to you. The record-breaking cold of the Boomerang Nebula, or the vast quiet cold of the cosmic voids between galaxies. Because now the story begins to lean toward its final question. We have looked at local cold on worlds, regional cold in molecular clouds, exceptional cold in the Boomerang Nebula, and the immense background cold of the spaces between stars, galaxies, and clusters. We have seen that emptiness and temperature do not always align, that some of the darkest places are not the coldest, and that some of the hottest gas in the universe can exist in regions that seem, from a distance, like nothing but blackness. So what comes next? The limit itself. If the universe can become this cold, if some places can approach absolute zero so closely, and if the future universe is expanding into ever deeper emptiness, then a final question begins to rise from all that silence. Could anything ever become colder than this? Could nature produce something even more extreme than the Boomerang Nebula? Could the universe as a whole keep cooling forever? What does absolute zero really mean, and why does it remain unreachable no matter how quiet, dark, and empty the cosmos becomes? That is where the journey turns next. From regions of cold to the idea of cold itself. From the scale of emptiness to the limit of stillness. And once we cross into that question, the universe becomes quieter than ever. Part 9. Could anything ever become colder than this? After drifting through shadowed craters, frozen worlds, dark molecular clouds, dying stars, and the vast quiet between galaxies, we arrive at the question that seems to wait behind all the others. How cold can anything really get? Not just in practice. Not just in some remote corner of space. But in principle. Is there a true bottom to temperature? A final floor beneath all motion, all warmth, all microscopic restlessness? And if that floor exists, could the universe ever actually touch it? This is where the story becomes quieter than ever. Because once you begin asking about the coldest possible cold, you are no longer really asking about places alone. You are asking about reality itself. About motion. About energy. About the way matter behaves when almost everything has been taken away. You are asking what remains when the dance slows so much that it nearly stops. And the answer, like so many answers in physics, is both simple and elusive. There is such a limit. It is called absolute zero. Absolute zero is the point at which temperature reaches zero on the Kelvin scale. In Celsius, that is minus 273.15 degrees. In Fahrenheit, minus 459.67. It is the coldest possible temperature in the framework of thermodynamics, the point where classical thermal motion would be reduced to its lowest imaginable state. Not ordinary winter cold. Not the cold of Antarctica. Not the cold of Pluto. Not even the strange deep cold of the Boomerang Nebula. Absolute zero sits beneath all of those, like the bottom of a well-known natural place has ever fully reached. At first, it sounds almost easy to imagine. If heat is motion, then cold is less motion. So keep taking energy away, and eventually the motion should stop. That seems straightforward enough. The swarm of atoms slows. The vibration fades. The restless collisions grow gentler and gentler until, at last, everything becomes perfectly still. But this is where the universe begins to resist the imagination. Because perfect stillness, it turns out, is not something nature hands over easily. In fact, according to the laws of physics, absolute zero cannot be reached by any finite process. You can get closer. Closer still. You can cool atoms to extraordinary extremes. You can reduce motion until it is almost unimaginably faint. But the final step, the exact arrival, remains out of reach. It is like a horizon that retreats as you approach it, not because the laws are teasing us, but because reality at those scales is stranger than the old picture of simple stillness. Part of the reason is quantum mechanics. Even when matter is cooled as far as possible, the universe does not allow every form of motion to vanish completely in the ordinary sense. There remains a kind of unavoidable trembling, sometimes called zero-point energy, a minimum quantum restlessness built into the fabric of physical systems. This does not mean objects stay warm in the everyday sense. They do not. But it does mean that the dream of perfect, featureless stillness is not quite the right picture. The deeper we go, the less the universe resembles a machine winding down to silence, and the more it resembles a mystery whose last whispers cannot be completely erased. There is something almost tender about that. It means reality never becomes entirely mute. Even at the lowest imaginable energies, something remains. A faint, irreducible trembling. A refusal to become perfectly frozen in the most absolute and literal way. And that brings us to a beautiful distinction. When we speak about the coldest places in the universe, we are usually talking about natural environments. Gas clouds, nebulae, shadowed craters. deep interstellar or intergalactic regions. But when physicists speak about approaching absolute zero, they often mean something far more controlled and delicate. Tiny systems in laboratories, trapped atoms, carefully engineered conditions. The scale becomes microscopic even while the concept becomes enormous. Nature, left to itself, gets very cold in some extraordinary places. The Boomerang Nebula can fall to around 1 Kelvin. Dark molecular clouds can sit near 10 Kelvin. The cosmic background itself is just under 3 Kelvin. These are astonishing numbers. But they are still not the end of the scale. Human beings, through careful experiment, have gone far lower. In laboratories, physicists have cooled atoms to temperatures unimaginably close to absolute zero, to tiny fractions of a degree above it. Not by putting them into some ultimate refrigerator in the ordinary sense, but by using lasers, magnetic fields, and exquisitely controlled techniques that remove energy from atomic motion. At such temperatures, matter begins to behave in ways that would sound almost dreamlike if they were not real. Atoms can merge into collective quantum states. They can lose much of the individuality we usually imagine matter having. Entire groups of particles can begin acting almost like one shared wave. This is one of the quiet wonders of physics. The colder matter becomes, the less ordinary it looks. Heat, after all, hides complexity from us. At higher temperatures, particles rush about, collisions blur patterns, and systems behave in more familiar, disorderly ways. But cool a system enough, and strange coherence can emerge. Quantum behavior, usually hidden by noise, begins to show itself more clearly. The universe does not simply become duller as it cools. In some ways, it becomes more revealing. That means the journey toward absolute zero is not a journey toward nothingness. It is a journey toward subtlety. And yet even in the lab, the exact endpoint is still never reached, only approached. This is important because it teaches us how to think about the question properly. Could anything ever become colder than what we have seen so far? Yes, in the limited sense that humans can create temperatures below those found naturally in space. But could anything truly reach absolute zero? No, not according to the deepest principles we currently understand. There is always another fraction to remove, another tiny remnant of motion, another final step that remains impossible. So what about nature itself? Could there be some even colder place out there, somewhere beyond the Boomerang Nebula, still undiscovered? The honest answer is yes, there could be. The universe is far too large for us to speak with perfect finality. We know the Boomerang Nebula is the coldest known natural place so far. Known is the important word. Astronomy is always working with incomplete maps. The sky is vast, and many of its structures are faint, short-lived, or difficult to measure. It is possible that somewhere else in the galaxy, or in another galaxy entirely, another dying star system has produced an outflow even colder for a brief time. It is possible there are other cosmic refrigerators we have not yet caught in the right phase. But there are reasons the Boomerang Nebula remains special. To get colder than the cosmic background, a natural system has to do more than simply hide from heat. It has to actively cool below the temperature that deep space itself is constantly bathing it in. That is not easy. It requires a process strong enough to outpace the surrounding background radiation, at least for a while. Rapid expansion can do it. Certain local physical conditions might do something similar. But nature does not create such arrangements casually. So while colder unknown natural places may exist, they are unlikely to be common. That, too, has a certain softness to it. The universe, for all its scale, still seems to treat the deepest cold as something rare. Darkness is common. Low temperatures are common. But record-breaking cold, the kind that slips beneath the background whisper of the Big Bang, appears to require something dramatic and precise. And then there is the larger future of the universe. If the cosmos keeps expanding, And if distant galaxies continue to drift farther apart, what happens to the temperature of everything in the long run? Does the universe itself keep cooling forever? In broad terms, yes. The overall universe continues to cool as it expands. The cosmic microwave background gets stretched to longer and longer wavelengths, which means its temperature drops further over unimaginable spans of time. In the very deep future, long after current stars have aged and faded, the background temperature of the cosmos will be lower than it is now. Lower than 2.7 Kelvin. Lower still after more time passes. But even here, absolute zero remains beyond reach. The universe may cool and cool and cool, becoming darker, emptier, quieter, and more dilute, but the exact final floor is still never touched. It is approached asymptotically, one might say, though that word is colder than I want the moment to feel. The softer way to say it is this: the universe can keep leaning toward perfect stillness without ever fully arriving there. There is something deeply poetic about that. A cosmos aging toward silence, but never becoming perfectly silent. A vast expansion toward cold, but never quite reaching the final bottom. It means the story of temperature does not end with a clean full stop. It trails off. It thins. It fades into a kind of infinite almost. This future picture is sometimes described as a heat death, which sounds dramatic, but in truth it is a story less about fire than about its absence. Over immense spans of time, stars burn out. New star formation slows. Galaxies exhaust easy supplies of gas. The great engines of light become rarer. Matter spreads. Energy differences flatten. The universe, in that far future, becomes less able to do interesting thermodynamic work because everything is more evenly diluted. It is not a bang. It is not an explosion. It is a long settling. And that settling is cold. Not because every local region is identical, and not because nothing at all can ever happen again, but because the broader trend is toward lower energy gradients, fewer bright structures, and a deeper surrender to expansion. The night sky, if there were anyone left to see it, would eventually look darker still. More galaxies would disappear beyond observable reach. The old background radiation would be colder and thinner. The grand architecture of the universe would feel lonelier. Yet even that does not mean perfect zero. The horizon remains. So the deepest answer to our question has two layers. Could anything ever become colder than the cold places we have discussed? Yes. In laboratories, under controlled conditions, humans have already created temperatures below those found in nature. And perhaps nature itself still hides rarer, colder phenomena than anything we have yet measured. But could anything ever reach the absolute end of cold? No, not fully. Not exactly. Absolute zero is less like a place one finally arrives and more like a limiting edge built into the logic of the universe. And perhaps that is fitting. The universe gives us many extremes we can touch indirectly through theory or observation, but it often keeps a final sliver of distance between itself and our desire for completion. Black holes hide their centers. The beginning of time hides behind opacity and theory. Quantum reality resists simple visualization. And absolute zero, too, remains not impossible to imagine, but impossible to fully attain. There is wisdom in that, if one wants to hear it. Not all limits are walls. Some are asymptotes. Some are gentle refusals. Some truths can be approached forever. This also changes how we see the cold places we have already visited. A permanently shadowed crater on the Moon is not impressive merely because it is cold by human standards. A molecular cloud is not impressive merely because it sits near 10 Kelvin. The Boomerang Nebula is not astonishing merely because it is around 1 Kelvin. These places matter because they show us different ways the universe leans toward its lower boundary. Different strategies of cooling. Different arrangements of matter, radiation, shadow, and time, all drifting toward the same unreachable floor. The crater leans there through shadow. The molecular cloud leans there through shielding and darkness. The Boomerang Nebula leans there through rapid expansion. The future universe leans there through cosmic stretching. And none of them, not even the oldest and largest structures, can quite finish the journey. That makes the universe feel less like a machine with a final off switch, and more like a process with an ever quieter heartbeat. If these slow explorations are helping you settle deeper into rest, you can gently support the channel by liking the video, subscribing, and leaving a comment about which idea feels more mysterious to you, that humans can make matter colder than most of space, or that absolute zero remains forever out of reach. There is one more layer to this question that is worth touching before we move on. What would absolute zero even mean emotionally, if it could be reached? We often use the language of cold to describe emotional distance, emptiness, silence, stillness. But physical cold is not sadness. It is not loneliness. It is not absence in the human sense. It is energy distributed differently, motion reduced, disorder changed. And perhaps this is why the cold universe feels so calming rather than frightening when approached slowly. It reminds us that stillness is not the same as death. It can also be order, clarity, simplicity, a quieter kind of existence. The coldest regions in the cosmos are not always empty of meaning. Some are star nurseries. Some are laboratories of strange quantum behavior. Some are brief monuments to dying stars. Some are previews of the universe's far future. Cold does not erase the story. It changes its pace. And in a sleep-like way, that may be the gentlest truth of all. As the universe cools, things do not simply vanish. They slow. They spread. They soften. The drama becomes quieter. The bright chapters become rarer. The intervals between events widen. It is less like a sudden ending and more like a long dimming of the lights in an impossibly vast room. So no, the universe may never truly touch absolute zero. But it can come wonderfully close. Close enough to make atoms behave like shared waves. Close enough to preserve shadowed ice for ages. Close enough to build dark clouds that cradle future stars. Close enough to let a dying star's outflow briefly fall below the background temperature of creation itself. And perhaps that is enough. Perhaps the meaning lies not in reaching the final limit, but in how many different ways reality can move toward it. Because the next and final step in this journey is not really about one more number. It is about what all this cold, all this scale, all this darkness, and all this near stillness say about the universe as a whole. Not just the physics of it, but the feeling of it. The emotional architecture of a cosmos where the largest spaces are quiet, the deepest temperatures are almost beyond imagination, and the brightest things we know are surrounded on all sides by a vast and ancient calm. That is where we go next. Not deeper into measurement, but into meaning. Part 10. The emotional scale of a cold universe. By now, the universe has changed shape around us. What began as a simple question about cold has turned into something much larger, and perhaps much quieter. We started with familiar instincts, with the old human image of space as a kind of frozen emptiness. Then the details began to unfold. We found shadowed craters near home that hide ancient cold. We found frozen worlds under weak sunlight. We found molecular clouds only a few degrees above absolute zero, drifting in darkness while preparing future stars. We found the Boomerang Nebula, a dying star's outflow becoming colder than the background of space itself. We found the great intervals between stars and galaxies, and the even larger voids where structure thins into silence. And after all of that, one feeling begins to linger more than any one number. The universe is not simply cold. It is deeply, overwhelmingly, beautifully quiet in most of its volume. That may be the deepest impression left by this journey. Not the specific record of 1 Kelvin, or the exact figure of 725 Kelvin, or the temperature of a crater floor hidden from sunlight for billions of years. Those details matter, of course. They are the bones of the story. But the larger emotional truth is something else. It is the realization that the brightest things in existence, stars, galaxies, nebulae, living worlds, are all suspended inside an enormous background of darkness and near stillness. Heat is local. Warmth is local. Light is local. But the larger stage is cold. There is something humbling in that, though not in a cruel way. It does not make the universe feel hostile so much as honest. It reminds us that our instincts were shaped inside one small pocket of retained warmth. We live beside a star. We breathe within an atmosphere. We move through air, weather, seasons, and oceans. Even our idea of night is softened by clouds, by city lights, by the ground beneath us holding some of the day's heat a little longer. Human life takes place inside a tiny protected layer of thermal comfort, balanced so delicately that we often forget it is unusual. The more we look outward, the more unusual it becomes. A planet like Earth is not the default state of matter in the cosmos. It is a rare local arrangement. A warm ocean under a bright sky is not what the universe mostly is. A forest at sunrise, a room with lamplight, a hand wrapped around a warm cup, these are not ordinary conditions on the cosmic scale. They are intimate exceptions. Beautiful exceptions. Small held notes of warmth in a much larger composition built mostly from low light, low density, and cold distance. That does not diminish their value. It increases it. Because once you begin to understand how much of reality lives only a few degrees above absolute zero, warmth stops feeling trivial. A star becomes more than a star. It becomes a shelter. A planet becomes more than a world. It becomes a delicate reservoir. Life becomes more than chemistry. It becomes chemistry that somehow found a way to hold onto useful warmth for long enough to wake up and ask where it is. And perhaps that is why the cold universe feels so moving when approached slowly. It reveals the background against which all tenderness exists. In a way, the universe teaches value through contrast. We understand warmth more fully when we know what surrounds it. We understand home more fully when we understand how much of reality is not home. We understand the miracle of a lit room on a living planet more fully when we know how vast the darkness is outside that room. This is not meant to make the cosmos feel lonely, although loneliness is one possible word for it. It is more accurate to say it makes the cosmos feel spacious. Spacious in a way the human mind rarely experiences directly. On Earth, even emptiness is usually still full of something. Air, sound, smell, gravity pulling against the feet. The subtle presence of walls, horizons, leaves, distant traffic, hidden animals, changing weather. Even a desert is rich compared with deep space. Even the stillest earthly night carries texture. The coldest regions of the universe carry almost none of that. A molecular cloud may be full of chemistry, but to human senses it would feel almost beyond sensation. A void between galaxies would not offer a horizon or a landscape. The Boomerang Nebula, dramatic in its physics, would still unfold in silence. The cosmic microwave background fills all of space, but not in a way our eyes can simply rest upon. So much of the universe exists in a form that lies beyond direct human feeling. And yet, somehow, through science, patience, and imagination, we can still approach it. That may be one of the most beautiful things our species does. We cannot survive naturally in the coldest parts of the cosmos. We cannot stand in a dark nebula or drift in a cosmic void. We are built for softer conditions. But we can understand those places. We can measure them. We can think carefully enough to reconstruct their character. We can imagine a crater that never sees sunrise. We can imagine gas drifting at 10 Kelvin. We can imagine a dying star throwing out its own frozen breath. And by imagining these things, we stretch human awareness far beyond the narrow thermal band in which our bodies evolved. In that sense, science is not only a way of knowing, it is a way of extending the mind into environments the body will never inhabit. And what the mind finds there is often not terror, but calm. That may seem surprising at first. One could reasonably imagine that the true scale of cosmic cold would feel frightening. The distances are too large, the temperatures too low, the emptiness too complete. But when approached slowly, when allowed to unfold in a gentle rhythm, the cold universe often feels less like a threat and more like a form of release. There is no hurry in it, no crowding, no noise, no traffic of urgent events pressed too close together. The vast cold structures of the cosmos do not rush. They drift, they wait, they hold. Even their violence often happens on scales so large and slow that, from a distance, it becomes almost serene. A star can die violently and still appear to us as a soft nebula. A cloud can gather the material for future suns over millions of years. A void can widen for ages beyond imagination. The cosmos is full of processes that would be catastrophic up close and peaceful from far away. Distance turns violence into shape. Time turns upheaval into architecture. And cold, perhaps more than anything else, slows the emotional tempo enough for us to see that transformation. There is another gentle lesson hiding here as well. Cold is often associated with endings. We speak that way naturally. Something goes cold when it is abandoned, when it is no longer alive, when the fire has gone out. A cold room, a cold body, a cold silence. But the universe uses cold for more than endings. Again and again, our journey has shown that cold can be a beginning too. Dark molecular clouds are cold, and they give birth to stars. Shadowed craters are cold, and they preserve ancient ices. The outer reaches of planetary systems are cold, and they store primitive material from early formation. Laboratory temperatures near absolute zero are cold, and they reveal hidden quantum states of matter. Even the future universe, however dim, is not just an ending in a dramatic sense. It is a transformation in pace, a spreading out, a softening of energy differences. So perhaps the emotional meaning of cosmic cold is not death alone. Perhaps it is incubation, preservation, silence before form, silence after form, the long interval in which one thing ends and another has not yet begun, or has just barely begun in darkness where almost no one can see it. That makes the universe feel less bleak and more cyclical. Not warm in the sentimental sense, but balanced. Heat and cold are not enemies there. They are partners. Stars ignite because cold clouds collapse. New elements are forged in hot interiors and then released into colder space. Dust survives in quiet regions until it is gathered again. Worlds form, cool, and change. The universe is not a simple story of warmth against cold. It is a story of each making the other meaningful. This is why the scale matters so much. If the coldest places were only tiny, their significance would feel smaller. They would be curiosities, little chambers of strange physics. But the universe does something grander. It spreads low temperatures across enormous distances. It lets cold become regional, structural, architectural. It lets entire clouds, halos, and voids embody that near stillness. It lets the background of the cosmos itself rest only a few degrees above the lowest possible temperature. In other words, cold is not a detail painted into the edges of the universe. Cold is part of the design. And once that becomes clear, everything else looks slightly different. Stars no longer appear simply as bright objects. They appear as interruptions in an immense dark calm. Galaxies no longer appear simply as collections of light. They appear as bright knots woven into a much larger cold web. A habitable world no longer appears simply convenient. It appears improbable, almost improbably tender, held within a narrow band of warmth between deeper cosmic extremes. Even time itself begins to feel different. On Earth, time is often experienced as pressure. Deadlines, decay, urgency, motion, noise. But the timescales of cosmic cold are so long that they soften the sharp edges of that feeling. A molecular cloud does not care about an afternoon. A nebula does not organize itself around a week. A void does not notice a century. These structures unfold in patience so vast that human anxiety begins to look like weather on the surface of a pond while the deep lake beneath remains still. There can be comfort in that, not because it solves our lives. It does not. But because it changes proportion. It reminds us that rest is not laziness in the larger logic of nature. Some of the universe's most important work happens slowly. Some of its most consequential structures spend millions of years in low-energy quiet. Some of its most revealing states appear only when motion is reduced almost to nothing. Stillness is not always emptiness. Sometimes it is preparation. And perhaps that is part of what makes these journeys fit so naturally into sleep. Sleep itself is not nothing. It is not blankness. It is a transition, a slowing, a state where certain forms of activity fade so other forms can quietly continue. The body repairs. Memory settles. The breath finds a gentler rhythm. Thought loses its sharp edges and becomes more fluid. In a soft metaphorical sense, sleep is our local version of what the universe does on larger scales when it cools. Not extinction, not erasure, just a different mode of being. The coldest regions of the cosmos invite that same kind of mental slowing. They ask the imagination to release its usual need for immediate action, immediate brightness, immediate answers. They ask us to drift instead, to think in centuries and light years. To sit with structures that do not care whether we understand them quickly. And in that sitting, the mind often begins to quiet itself. This may be why cold space has inspired so many human feelings at once. Awe, yes. Fear, sometimes. Loneliness, perhaps. But also wonder, relief, and a kind of clean stillness that is hard to find in ordinary life. The universe at low temperature does not flatter our importance, but it does offer perspective. It says, in effect, that the world of noise and urgency is not the whole story. Beyond it lies an older and larger calm. Even the cosmic microwave background, that faint relic glow from the early universe, carries that feeling. It is ancient, gentle, nearly uniform, and always present. Not visible to our eyes, yet washing through every room, every city, every mountain, every ocean, every human life. The oldest light in existence moving quietly through everything. The thermal memory of the Big Bang now reduced to a whisper. There is something almost impossibly peaceful about that. The beginning of everything did not vanish. It cooled. It softened. It spread out until it became the most delicate background imaginable. In a sense, the universe itself has been settling for 13.8 billion years. Not rushing toward some dramatic answer, but expanding, cooling, changing pace. And here we are, on one small planet, alive long enough to notice. That may be the most extraordinary contrast of all. A warm, thinking species emerging inside a vast cold cosmos and becoming aware of that contrast. Matter holding onto enough energy, enough structure, enough continuity to ask what lies beyond its own little shelter. The universe contains cold clouds that may birth stars, and it also contains beings who can understand what a cold cloud is. That is not a small thing. It means the cold universe is not only scenery. It is part of the story of consciousness too. Without the larger cold background, stars form differently. Galaxies evolve differently. Planets may not arise in the same way. And without stars and planets, there are no eyes to look out, no minds to wonder, no quiet voice late at night asking how cold the universe can become. So even the deepest cosmic stillness plays a role in the existence of thought itself. Cold is not outside the story of life. It is one of the conditions that helped make life's larger setting possible. That thought brings us gently back to where we began. The true scale of the universe's coldest regions is not just measured in kilometers or light years, though those scales are already staggering. It is measured in significance, in what those regions tell us about the structure of reality. They tell us that most of the cosmos is not warm, busy, or crowded. They tell us that light is precious partly because darkness is so abundant. They tell us that some of the most important places are not bright at all, but hidden, cold, and patient. They tell us that the universe does not fear stillness. It builds with it. And perhaps most gently of all, they tell us that quiet is not the absence of meaning. A shadowed crater can preserve ice. A molecular cloud can hold future stars. A cold laboratory can reveal quantum truth. A dying star's outflow can briefly become the coldest known natural place in the cosmos. A vast void can make the brightness of one distant galaxy feel miraculous. Quiet, in the universe, is often where meaning waits. If these slow explorations of science and deep space have been keeping you company tonight, you can support the channel in the simplest and calmest way, by leaving a like, subscribing, and sharing in the comments where you're listening from, or which part of the cold universe stayed with you most. It is always quietly wonderful to imagine these thoughts drifting outward from one room to another while the night settles around us. And now, as the journey comes to rest, it is worth holding one final image. Not the Boomerang Nebula alone, though it is unforgettable. Not a crater in permanent shadow, though that too is beautiful. Not even a giant molecular cloud, drifting at 10 Kelvin while stars gather invisibly inside it. Instead, picture the larger whole. Picture a universe full of scattered lanterns, stars, galaxies, brief brilliant chapters of heat and light, all suspended inside an ancient and nearly frozen background. Picture the light from creation itself stretched thin across all of space. Picture dark clouds hiding future suns. Picture lonely intervals between galaxies. Picture the quiet patience of structures that take millions of years to become what they are. Picture warmth not as the default, but as a precious local event. Picture life as one of those events becoming aware of itself. And then picture all of it continuing. The stars burning where they can. The clouds cooling where they must. The voids widening. The background glow softening. The universe, in its own vast way, breathing outward into greater stillness. Not dead. Not empty of meaning. Just immense, calm, and older than any emotion we usually carry into the night. That is the emotional scale of a cold universe. Not merely that it is cold, but that its cold is large enough to hold everything else inside it. And maybe that is why, when we look long enough into the deep sky, the mind sometimes grows quiet too. Because somewhere beneath all the numbers and all the names, the cold universe is offering us a kind of perspective that feels almost like rest. A reminder that brightness can be brief and still matter. That stillness can be vast and still gentle. That the background of reality is not noise, but silence. And that even in a cosmos where most regions are dark, thin, and near frozen, there are still stars. There are still worlds. There is still warmth. And, for a little while, there is still us, awake enough to wonder, and tired enough to let that wonder slowly carry us into sleep.